Ladies and gentlemen, and dear colleagues and friends, please allow me to use this opportunity to introduce Professor Alan for this wonderful talk. But before that, just a small advertisement for the Artificial Intelligence Chemistry Journal. And I really hope people and you can support us by submitting your paper and also act as a referee for our journal. And thank you all for this service. Okay, then I can use this opportunity to introduce Professor Alan Aspros Guzik for his wonderful talk. Actually, he is famous in this field, and his prestigious work about artificial intelligence design, artificial intelligence-driven reverse design of materials, as well as his wonderful work in quantum computing has impressed us a lot. And he conducts research in the field of quantum information, chemistry, machine learning, and interface chemistry. And currently, he is more interested in the automation and autonomous chemical laboratories for accelerating scientific discovery. Yeah. So please, Professor Alan Aspro Guzik, please give your wonderful talk. Yeah. Thank you.
Thank you, Yun. I really appreciate the invitation. I'm going to share my screen. I was told to speak for 40 minutes, so I'll try to do so. Let me just, give me 1 second. Let me just put this in full screen. Give me 1 second. Just 1 second. Present from current slide. Okay. Well, I don't know why it still has this button. Okay. I'll do my best. There's still a browser there, but we'll do it.
Okay, we can see that. Yeah.
Yes, excellent. Let me just try to zoom in like this. Perfect.
That's good.
Okay, and I will also put my timer.
It's 40 minutes, yeah.
Yes, just to make sure, I don't want to mess up. Okay, so June, it's an honor to be here, also to see old friends like Joel, and of course many others that I will meet when I visit China for the first time very soon. So today I will tell you kind of my view of AI-driven materials design, and I will use examples from my research group, but also I will talk about the research of others. I mean, the main motivation of this field, I think, one of the main motivations of this field is the deep problem of discovery and translation, right? You take a molecule or material, by the time it actually is used in the world, the time scale is actually 10 to 25 years. Okay, so I am gonna begin with one example of that, and that example has to do with poop. This is the poop of birds. This is guano, and before the discovery of the nitrogen fixation process, fertilization required import of export of tons of guano all over the world. Okay, and it was the visionary work of Haber and Bosch that over 20 years actually allowed for the screening of different catalysts until they developed, of course, the Haber-Bosch process and really transformed humanity. The reason I like to always begin with this nowadays is because they actually parallelized and they were screening 50 to 100 materials per week using high school teachers. That was the robots at the time, okay? So incredible development. And if you want to think about how incredible is that development, I want you to remember the movie Avengers Endgame. In the movie Avengers Endgame, at the end of the movie, half of the people disappear. Okay? Thanos decides to press a button and then, uses the globes or whatever it is, and then disappears half of the people. That would be exactly what would happen if somebody disappeared the nitrogen fixation catalyst from Earth, right? We're just hearing actually from the war in Ukraine, because Russia and Ukraine are exporters of fertilizer, the biggest problems that we have in the price of food. So we have disruptions in the supply chain, and that's just an example of how important is a single material for humanity. Okay, so obviously, let's talk about other materials. This is one that is going to be related to my talk, so it's important to kind of mention it. OLED. China is big in OLED, BDC, many companies Xiaomi, all these different cell phones actually use OLED display technology. Okay, and OLED is actually closer to our lifetime. OLED technology was discovered when I was 10 years old in 1987, and I was able to, through my life, I guess, or through anybody's life, see the development of OLED. Right? It was a paper when I was 10 years old, right? And the first phone of Samsung came out in 2007. Okay. And now, of course, the OLED market keeps growing and growing and growing, right? But you can see there how long it took from the discovery to the optimization to the patenting, right? So now the company that sells most of the OLED materials, actually based on the technology of Stephen Forrest, Dan Princeton, is a strong buy by the time I did these slides. I don't know with the stock market nowadays, but at the time I made these slides was an $8 billion company with a price earnings ratio of 40, okay? So this is an IP-based company. They own the IP for materials, but it still took them 30 years to commercialize the OLED. So just imagine out there in chemical space, how many other materials are lurking to become multi-billion-dollar industries. So the reason I start with the story of OLED is because my own adventure with the AI actually started with OLED. When I was at Harvard and I was hired on for Samsung to explore these compounds called temperature-assisted delayed fluorescence compounds. These are compounds that have a very near resonant triplet and singlet states, and therefore allow for the thermally activated intersystem crossing from the triplet into the singlet, and therefore have very high emission properties. At the time I was working on this, 2012, 2013, there were very few known. And what we did with AI and screening was able to actually find out about 30 good candidates, out of which we made we made 30 candidates, and then out of them 3 were actually good enough to put in a Nature Materials paper. Now, this used AI as a screening tool and allowed us to do things 10 times faster. Why is that? Because at the time we needed to use 100,000 molecules to train the system, and then we executed the system on the remaining 900,000. So it's roughly a factor of 10 speed up at that time. But that got me into the idea of, and it was at the time that Trump was elected, I was leaving the country, and a good time to reinvent yourself. So the Canadians were kind enough to host me here in Toronto, and as part of my move, I was able to build a lab, okay? And why I wanted to build a lab is because if you see this funnel, it's pretty depressive, right? We can make millions and millions of molecules in the computer, but we can only literally make very few devices. And that is the reason why, even if we just use AI, we won't be able to actually accelerate the traditional materials discovery cycle. So we started working alongside many others, pioneers like Benji Manujama, on the concept of the self-driving lab, okay, which is a laboratory that as soon as it generates data, uses the data to iterate back and actually design new materials as you go. So it was a great opportunity to actually start getting into this field. And around the time actually I was leaving, I wrote this paper, okay? I think this paper was published just a few months before I changed countries, with Roland Lind and Markus Reichert, two very, very cool quantum chemists, friends of mine. And in that paper, we had a vision. We were thinking about what would be the future of chemistry in theoretical chemistry. So I'm going to start with that just as a big vision. I know I'm opening this workshop, so I think it's always good to think about that. So I want to tell you what I think the 21st century is going to be all about. These, according to the World Economic Forum, are the technological and economic drivers of the 21st century. Up to here, up to 5. I added 3 that are more scientific, that are my choices, right? Digitalization of matter, control of molecular biology like CRISPR, and disruptive computing like quantum computing. This is just my favorite ones. But I argue that these technological drivers are the ones that actually make us advance, right? We're talking about AI. June talked about his new journal. I know Joel does AI research too. He actually published a paper in our journal, so thank you about that as well. And but the point here is we are using AI because commodity GPUs made AI possible. At the same time, the commodity GPUs were made possible because of video games. In the room next door, my kids are playing video games right now, literally. Okay, So we have to think about as theoretical chemists, what are those drivers, right? How can we use the blockchain? How can we use robotics, right? Robotic arms are decaying in price exponentially, okay? So, sorry, there's a problem here. What's happening with my presentation? Okay, there are some problems with the slides. So my idea is that where we wrote, Roland and Marcus and I wrote that this is kind of like the mission statement of the 21st century theoretical chemistry. It's kind of like the city of chemistry. You will ask a machine, can you please answer this chemical question? Okay? And it will be able to show it to you, maybe even in virtual reality. Right? So this is kind of an extension of the 1950s ideas of quantum chemistry, where we asked questions with Hamiltonians and we got energies or properties. Now we're trying to ask more important questions like products of chemical reactions or retrosynthesis pathways. Not more important, more complex questions that require more data. Sorry. This is an example of a dialogue that I imagine one could have with a robot in the next decade or so, right? A robot called Organa, you will ask it, I would like to make a molecule, and you can read what I'm thinking. I want you to make an OLED. Organa will say, okay, I'm going to try to buy some compounds to actually do combinatorics and make a library. And then I can show you the results later. What are the colors, what are the oscillator strengths, etc. Okay? So that's an example of and I'm just going through the discussion here between Jane and Organa because I don't like to read slides, but it gives you an idea of the kinds of things, right? Could you please order 20 and then let's test them, right? So in this paper, we thought that there are 6 challenges for this century, okay? And we wrote it 5 years ago, and I think it really stands as the challenges, and people are actually made tons of progress solving these challenges. So one challenge I call the designer challenge. We'll talk about it today. How can we go from property to molecule? We became the experts on the last century from structure to property, right? You give me a structure, I can give you its hyperpolarizability, I can give you its potential energy surface, I can give you its excited states, right? But if you ask me, make me a molecule that is green and has a high oscillator strength and has this and that, can we use a model that actually gives me the structure based on the property? And that's what is called inverse design. And generative models are a very important tool, and we'll come back to them. GPT-3, large language models, very important. When we wrote this paper, I never imagined GPT-3 was going to be so powerful. Actually, my research group is working on a project related to GPT-3 as of last week. We just started a project. And what is interesting to me is, can we ask Android questions that they tell us, right? But I believe we're going to need actually logic-based AI. I'll come back to this at the end of the talk. Another question, this is related, to my obsession with quantum computers. We invented this idea in this paper of what we call the Feynman test. Because Feynman used to say, like, if you have a quantum simulator and you use the quantum simulator, if you measure properties of the quantum simulator, they will be identical to that of the physical world. Obviously, that's assuming a very large basis set. But a quantum simulator gives you full CI energies in polynomial time, right? So it is possible in one day that maybe we will be able to do exact simulation as nature. And that's a vision of Feynman. I call it the Feynman test. I've been working on it for the last 17 years, and I'm very excited about the project. And finally, this idea of the self-driving laboratories. I like this quote by a pioneer of quantum chemistry, Perolov-Levdin. It says, one of the ultimate goals of electronic structure is the prediction of substances that have a particular property to mankind. 1957. So we're just trying to fulfill the vision of somebody like Perolov-Levdin. Okay, and obviously I was very interested, and I'm interested in augmented reality. Many people have done incredible work on this space, like Marcus Reicher himself. Okay, so let's talk about the designer challenge again, the inverse design. What's happening here? Sorry, my slides are a little bit messed up. I don't know why. This paper here is now my most cited paper, second most cited paper. Right? Only in the last 5 years, actually, it became really used because it was perhaps the first AI paper for chemistry that shows inverse design in the sense that you take molecular structures, encode them and decode them through a tool called autoencoder. It's basically a dimensionality reduction technique that has a very important property. Once you reduce the dimensionality, you can reconstruct what comes out of it. It has connections to encryption. It has connections to communications channels. So in this two-dimensional space, we were able to put basically drug-like molecules. And with this neural network, we were able to actually optimize the property and invert which molecule in this latent space corresponds to a particular property. Okay? Generative models became, this is the reason I'm telling you, that's my second most cited paper, right? I mean, the other one is on AI too. So, and this work tells you that, you know, generative design can be done with almost anything. Obviously, evolutionary algorithms were used in chemistry way before what I just showed you. Okay, and the modern version evolutionary strategies are really incredible. Okay, so I don't really care too much which generative model you use. They had to be used in different contexts, but they all allow you to solve the inverse design problem. That is the big deal about genetic algorithms. And we had this review paper last year with Robert Police. Talks about this thing. So you might say, well, Alan, where is the proof in the pudding? Well, MIT Technology Review called this one of the 10 breakthrough technologies 2020. The breakthrough technology was given to AI designed molecules. And the work cycle was this work with Alex Shaborankov and myself. I collaborated with them. They're actually a China, Hong Kong based company called In Silico AI that I will come visit later this in the fall. I collaborate with them in their SAB. And together with them, we wrote this paper where in 46 days, we used generative models to design a lead candidate for a drug. Now, In Silico has several drugs in stage 2 clinical trials, a couple in stage 2, several in stage 1, and so on. Okay? So In Silico AI, this drug was not in stage 1 or stage 2, but the drugs that they followed are actually doing that. They're doing extremely well. And all the top pharma companies, I would argue, have an AI for drug discovery program now. So let me just tell you some thoughts. This talk has some thoughts interspersed with some science on inverse design. What are the things that matter more for inverse design? I would say the ethics of inverse design will be very important. There was a paper about inverse design of poison. So I'm very worried about ethical use of these models. And very, very important is right now we're just making molecules. We need to start designing devices. And we also need to figure out how to do these things globally. I'll tell you a little bit about these global aspects in a little while. For the rest of this talk, I'm going to talk about what I like to call the matter computer in that review paper. Now people call it the Chemputer, chemistry computer. That's Lee Cronin. Or also a traveling lab that basically makes molecules. And I argue that we theoretical chemists are now poised to control experiments because everything is being automated. So experiments can be thought of as a GPU, and we can program them with Python, right? So we can now make damage, right? So I predict there's going to be a more and more blend between theory and experiment. Okay, like the barrier between theory and experiment is going to be broken. And but I always like to go back, right? I've been telling you about Levine. I like to think about the early stages. So, and the first, I think, relevant chemical automation paper was by Merrifield and co-workers. They automated the synthesis of peptides, which transform biology, make biology a digital science. Way earlier than chemistry, by the way. The biologists have beaten us to that because the building blocks are simpler. They have only amino acids, sugars, and RNA, right? And DNA. So this machine that I showed you before gave the Nobel Prize to Robert Merrifield because they were able to synthesize sequentially peptides in a machine and revolutionize biology. So how about chemistry? What is the first self-driving lab paper that I know in chemistry? So this paper was published when I was 2 years old by Winkow from S&K. At least of last year, Winkow was alive. A reporter that interviewed me found Winkow retired somewhere in New Jersey. Okay, so she spoke with him and he was very happy to talk to her about her 16-bit basic-based reaction optimization robot with robotic pumps at S&K, right? So the ideas that I'm telling you about hark back. What we have now is the technology to do them, you know? It was around this time that Feynman proposed a quantum computer, and this is when we're talking about quantum computers. And you see this time scale of technology is incredible. So in 2019, we put out this paper on the idea of what is a self-driving lab. We talk about the coexistence of experimental systems and robots, and also to distinguish it from high-throughput screening. The important thing about the self-driving lab is that you get very few data points at a time, or a reasonable number of them, and use those data points to steer in active learning the next stage of your experiment. So now, for the students in the room and for the people that want to learn about the field, I will argue some of the things that computational and theoretical chemists could work on in self-driving labs are shown in this slide. Experimental planning techniques, Bayesian optimization, bias corrections, HPC and quantum chemistry, obviously, automated experimentation, etc. These are all the things that I think we all need to build as a community to enable the self-driving laboratories. So now let's talk about my own lab, self-driving laboratory, and its results, which a lot of this is still unpublished. We're about to finish this year because it's an epic Manhattan Project style idea, right? So we wanted to pick back in 2017 a material that was just becoming possible, okay? But this story starts, obviously, again, about 10 to 20 years before, when I was a grad student in Berkeley in the early 2000s. There were many news about this guy called Hendrik Schon. Hendrik Schon is perhaps the biggest fraudster in the history of chemistry and material science. The guy was saying that he got a superconducting, pentacene crystal, and that he had all sorts of lacing crystals, and they were all fake. Okay. At the time, there was a postdoc in Princeton, Professor Chihaya Adachi from Japan, which was trying to replicate the fake results of fake Hendrik Schon. Now, parenthesis, I recommend you to buy this book and read it. Okay, Plastic Fantastic. It's a great book. To tell you the story about that, many people at Bell Labs that were involved in actually discovering the huge fraud. The huge fraud. So Chihaya, it took Chihaya almost 20 to 30 years later. Just in 2017, with Professor Mamada and Chihaya, they started discovering long-lived, not yet for a device that you can buy in a computer, but long-lived organic laser. So why would you like to have an organic laser? Well, think about it. This is an organic light emitting diode, incoherent emitter. Think about now putting cavities and now emitting coherently. All the crazy things you can do. Low light emission, detection. The technology will be incredible. So these are the molecules. Think about their electronic structure. Right? Quasi-resonant donor-rich acceptor type molecules, very large transition dipoles, actually super large transition dipoles, very hydrophobic, hard to synthesize. So we said, let's make self-driving labs for them. Okay? So this would not be possible without the two things: the money. DARPA can send money abroad, and I am a PI of a very large DARPA grant in Canada. And the 4 co-PIs here are equally co-responsible for this mess. We call this madness, okay? And it is madness because it was really like a big thing to do at the time, and we really needed the skills of this group of these 5 gentlemen, okay? So without Marty, Lee, Bartosz, and Jason, what I'm showing you is not possible, okay? So the general screening strategy, this is an outdated slide, it's actually very idealized, where we take molecular blocks. From that, we build a synthesizable chemical space. We don't use retrosynthesis. We use forward synthesis. Define a chemical space from our blocks. Use quantum chemistry, TDDFT, calculations of that sort to lower down to the things that matter. And then we do experiments, about 50 per day at that throughput. In reality, we make, in a good week, 100 or so for many reasons. But still making 100 organic lasers a week is many more than all the molecules that Chihaya Adachi has ever made, as I'll show you. So how does our lab look like? So, I was a new theory professor, so they gave me just one room, which I've been crowding, okay? So my self-driving lab room is crowded, and I'm happy to announce that the University of Toronto is going to build an entire building now for these things. But at the moment, there's only one room full of my own self-driving lab and many other self-driving labs in Toronto and other people's labs. So we became kind of like one of the meccas of that, actually, as a university. It's recently, in the many few years. And we have been hiring in this place, by the way. So we just hired Anatol von Lilienfeld. We hired Jason Hadrick Simpers. which is an experimentalist, and stay tuned for our new senior hires. I cannot tell you who they are, but I think you're going to hold to your chairs, okay? So anyway, what we do here is we synthesize with the ChemSpeed, characterize with HPLC, and separate with HPLC, and then characterize with lasers. Because to test if a molecule is a laser, you need to lace it. You need to measure its time resolved fluorescence. You have to measure its absorption and emission profiles. You have to measure its excited state absorption. And we can do this all in line from beginning to end in a weekend. So this paper just appeared last year in Advanced Materials. They gave us the cover, so this is going to be appearing soon. And you can see here, in this paper, you will see all the details of the experimental system. But what we did to demonstrate, this is the Hello World experiment, like the hydrogen potential energy surface of what we do. Let's put it this way. We did one run with 40 cores and one cap. Okay? And we just ran 40 lasers. Just to show that the system works, and here it is, our powder dosing self-driving laboratory. This is an Australian company called Trajan. This is the most expensive salt and pepper shaker ever used in history. It just shakes extremely precisely these little powders into that particular balance, and just admire the precision, right? So many significant digits of weight, very important for catalysis. All those powders, by the way, have RFID detection, so you can place them anywhere you want. Okay, but who am I to talk to China about robots? I argue China is more advanced on robots than the United States. So you guys probably laugh at our very primitive Canadian and US robots. Actually, this is an European robot. It's a ChemSpeed. Old technology, but it's actually very good at baking and shaking chemicals. So what you're seeing here is powder dispensing, top-down powder dispensing with less precision than the one I showed you. But also you can see here on the left the reactors. Okay, these are the reactors that basically are kind of like an Instapot of organic chemistry. There is a tube here in the back that will allow us to actually, after 12 hours or so of reaction, take out the compounds. Okay, and I'm gonna skip this animation, but it gives you an idea. So this is perhaps one of the most important plots in my life, because I started when I was young as screening organic photovoltaic materials, and I started screening organic flow batteries and many organic materials over my career. But what I always wanted is to be able to do the experiment as well. And what you see here is the wavelength. We don't care too much about the color, but it turns out our materials are at a pretty good wavelength, like blue-like. And this is the cross-section gain, right? How many molecules re-emit light and lace, okay? Per unit, per area of illumination, okay? And what you can see here is the state-of-the-art molecule of Chihaya. And what you can see here is in solution, just those 40, I guess the library was very well designed by my students and postdocs, we already have better molecules than Chihaya. So in one single weekend, we made 4 times more molecules than ever published in the field. And here is a device. We actually sent molecules to Chihaya, and you can see here the narrowed down fluorescence of a molecule, which shows you its lacing. And this is the excitation energy threshold, which needs to be lowered by device optimization to actually make these molecules better. Okay, if this threshold was smaller, these molecules could be devices today. So, but DARPA told us, you're running out of time in your DARPA project, you have to show us more results. So we developed what we like to call ACDC. That was the project that we developed this year. Okay, and what ACDC required is new methodology. So this is a paper that just appeared in Science in October, led by my friend Marty, okay, and then Bartosz Żywowski and myself. Bartosz was cut off from this, but Bartosz is in between me and Marty here. But Bartosz was more relevant to this paper than me, actually. He did more work. But what we're doing in this paper is using AI to optimize generic Suzuki conditions. So we took a big library of Suzukis. We used Marty's robots to optimize what is the best coupling reaction that doubled our yield of our reactions. So we had to take a side tour. We got a science paper on the side, which is pretty nice, but to be able to make our robot more efficient. So we do a 2-step, 5-component, 1-pod synthesis, which, because the audience here, I'm not telling you too much about the organic chemistry, But what I show you that is kind of cool is the idea of making software for all of this. This is our database as of 6 months ago of the organic lasers we had synthesized. You can see there, you can add users, you can remove users, you can store the spectra. But what is very nice is that we have the robots on all the labs, and we track who is making what, because we make some things in Urbana with Marty, and we make some things in Toronto. And some of the ligands are made in Glasgow, and some of them in Vancouver. And to make things even more interesting, we ship the purified molecules from Vancouver to Kyushu in Japan to actually make the devices. So this is the global freaking laboratory, right? So you can see here all our software, right? Fragments and what is available in what computer and how does the molecule look like. And this is of course by hand, but you can do it by API. You can actually control this system. And the AI actually drives it, right? The AI will tell the people what are the next compounds to make. Extremely complicated project. Again, I keep talking about it and we're almost close to finishing the main results, but this is how we were in January. This is 4 iterations, or I guess 2 iterations that I'm showing you here. All the different points. This is Chihaya's molecule, and you can say all of these molecules you see here are already better than Chihaya in terms of cross-section gain. And now some examples of something related to physical chemistry. These are these are not really our top structures. Some of the top structures have the zigzag property. Chihaya never thought about the zigzags. So this is where actually AI can help us like learn new things, right? So like, why are the zigzags better? Of course, this is going to be an interesting work for physical chemists, for myself, for any other people, because we're finding new classes of molecules that can lace, right? Those molecules that you saw are perhaps the brightest molecules that exist right now, okay? In terms of emission times and absorption cross sections. Those things, you have a drop of it and you put it in the dark room and put a little bit of a UV light and it will look like a discotheque, okay? So I want to end this talk by the future. I have 10 minutes and I will talk to you about what will be happening 10 years from now. The things that my lab is doing towards that, but also, of course, early stages of it. Okay? So, this paper took us 3 years to write. Started with a series of launches in the University of Toronto Faculty Club before COVID. So, I took my guys every week and gals, and we sat down and we thought about how crappy is AI now? What do I mean by that? Yeah, it's great. We have data and we use the data to find correlations and we do inverse design. But the AI doesn't tell us why it happened. The AI doesn't tell us the concept. It cannot tell you that it discovered a superconductor. Okay? So we wrote in this paper and we actually interviewed 80 to 90 scientists. I forget the number. We sent emails to Anastasia Alexandrova at UCLA and to all sorts of people all over the world. And we asked them, how have you learned new concepts from your computer? And people responded in these 2 classes. In the 1950s, Bernie Adler and many others started the field of molecular dynamics. In the 1940s, 1950s, say Samuel Boyce started quantum chemistry, interest in statistical mechanics. Widom, all these people taught us how to use the computer as a computational microscope. I mean, what we are doing nowadays, many others, Anatol von Lilienfeld, myself, many others, we're doing, and of course many people in this room, we're doing this second. We look at trends with statistics and we find new things like my zigzag molecules. But then the computer never explained to me what the zigzag molecules mean, right? So that's number 3, agent of understanding. So and in this paper, we went to read the philosophy of science to understand what the philosophers of science think about what is understanding. Because we need to understand that to actually tell you what understanding is, basically. But basically, understanding is the following. Is understanding a qualitative consequence, right? If I don't take a bath, I'm going to be itchy. I'm trying to teach that to my kids with very little success, right? If I don't take a bath, I'm going to be itchy, right? Why is that? There's bacteria in my skin. I'm going to get pimples. All those kinds of logical things that we're thinking about are concepts. They are not just correlations in a data set. So we need to build machine learning systems that understand the concepts and apply them to a new context. right? So if you see a dog that is very itchy, maybe you think maybe the dog needs to take a shower, maybe the dog has stuff in their skin. That would be an extension of your own experience of being itchy, okay? Second is to demonstrate that something is understood, you have to explain it. And if all of us are teachers and professors, we know it's true. I think the only time I really understood many things in quantum mechanics is when I had to stand in front of a classroom and teach them to other people. Okay, that's when I was like, oh shit, what the heck is a Klebsch-Roden coefficient? Like, that was the first time I really understood what it was, I guess, as much as I can, because I had to explain it to somebody else. But it's not enough that a computer understands these concepts. She or it or he will have to tell us what the concept is in English or French or Chinese. Okay, so those are the things that we wrote in this paper. Okay, so I think it's important to think that way, because I don't think we should all be working on deep learning. We have to start thinking about beyond deep learning. Okay, so that's kind of like a call for arms for the community. So now, in last time, I'm going to tell you what I think is going to be the lab of the future. Obviously, I heard from my friends in Silico that now there are these in China, there are these robots that bring you food to your room. Right? It's like Uber Eats, but real Uber Eats. Like, we have a primitive version with humans. In China, there are automated things that bring you your noodles or something. Well, that are mobile robots, right? These robots that we're thinking about are still not mobile, but they can see. And this is where we're getting state-of-the-art papers in computer science, not because of me, but collaborations with my computer science colleagues in Toronto. One of my demands after I moved here was to be a member of computer science, so I could be able to do this. So I'm a faculty member in computer science, so I take advantage of that. So this is a robot that is taking photos of that transparent glassware, and we published that last year as the best computer vision system for transparent objects filled with liquids. Why? Because we're trying to do, this paper in Coral was the record in 2021, and in 2022 we already are publishing beyond that, work on detecting where and how are transparent objects. Why is that so hard? Because the sensors have multiple reflections and transmissions. So the sensors get messed up. So you need to integrate many different sources, colors and depth sensors together. And the latest work that we did is this work, which is called MB-Trans. We were just having group meeting yesterday talking about it. It's our multi-view perspective transparent object system. We actually trained it on a virtual world that we rendered, like if it was a video game, to augment all the photos that we have in the laboratory. We also use them, but this is a very complex system that, if you really ask me all the details about it, I will tell you my two co-PIs know much more about it than me. But what we're doing here is multi-view, the same way when you're trying to figure out what something is, I will be able to look at this glassware from different perspectives. Okay, so all the engineering for doing that and the science is here. And the other thing that my student Naruki is doing, and this is the kinds of things that chemistry students do nowadays, is he's optimizing the movement of our robotic arms so they don't spill water. Very stupid, right? But now we don't need to spill water. Okay, and why are we doing this? Because we believe that the robots that I showed you before are too primitive. We want a robot to walk into a room, start picking up glassware and start doing experiments wherever the glassware is. Have a model of the world and start doing chemistry with the glassware, with all the things that we know. I forgot to tell you, you might have seen some QR codes here in the training. These are just for training. They are removed in the actual execution, right? That's what we're integrating in this year, so that we're able to do this. And the application that is going to be first application is cocktails. So we're working not on chemicals, but actual cocktails. And we are doing machine learning in the cocktail space. And I'm proud to tell you that we predict we're going to be able to do 3,300 different cocktails with this robot, out of the 5,500 or so that are in a cocktail database online. So the other thing that my student Naruki is doing, and I'm going to end with this, is, excuse me, what is the Naruki stuff? This is all a mess. What is the Naruki stuff? Yeah. So we are doing what is called, I don't forget how it's called. Excuse me. It's a terminology in robotics, but it is a task, so to speak. I'm forgetting the technical term. but the task that we're learning is pouring. So we are publishing papers on pouring. And what Naruki did over the weekend, over the Christmas break, is pipetting. So now we can pour and we can pipette, and we take the KDL, which is a language that Lee Cronin has for chemical robots, okay? That we augment it, map it to the task and motion planning that I told you about, and the PDDL optimization so that the thing actually doesn't drip the liquids, and then we connect it via robot operating system to actual chemical labware, and integrate all of it. So I have a computer science lab that cannot deal with chemicals, but can deal with salt and liquids and powders because it's in the computer science department. And you can see here actually Naruki's work on making sure that things are not constrained. Look at this. He's going to be throwing a bunch of stuff in the floor. And right now we have a kind of crappy precision, but we're able to do recrystallization experiments. And we're about to submit the paper with this. But of course, to increase the precision, this paper is submitted. The next paper will have very good precision because we built a robotic pipette that allows this thing to do things better. A primitive version of that is that squeeze bottle over there, but obviously now we have a proper 3D printed pipette that this robot can pick up. So I think, I don't know why my slides are all messed up here, totally messed up. I think that's going to be the future. Self-driving labs are going to move to vision-controlled robots, okay? That are going to know where things are, are going to be able to pick them up. And for cocktails, I think we are ready to do that by the spring. What I mean by that is we have papers on all the elements, but we're integrating right now, okay? And that later will become radioactive chemical management, right? And then it will become organic chemical reactions in the labs that require, for example, late-stage fluorination in pharma and so on, right? So I think this is going to be very important. We just put the paper out also in hospitals. Can you detect if an IV bag is full or not? This is the same technology. So we applied it for the COVID problem. And with that, I'm just going to end because these are my graduate students and postdocs. These are the people that really did the work. These are our pre-COVID photos, and these are our recently, just last Christmas break in Ontario. A lot of the robotic work was done by Hao Peng here. Who else is here? Robert Policho, he was gone already, but a lot of the people that did the robotic work were gone already on the paper that I showed you. But the people that are doing the work now, for example, Wishertian, etc. Okay, so on that, I'm going to just end, and I think I have some time for questions, perhaps. Thank you very much.
Yeah, thank you, Professor. A really amazing talk. Introduce us the history and also importantly draws the picture for the future lab and the future chemistry. Very exciting. Thank you.
Thank you.
Please.
Do we have time for questions? Do we have time for questions? Okay, good.
Yeah. We have 10 minutes for questions, and maybe 7 minutes. For questions.
Okay. Please. Don't be shy, people.
And actually, I have collected the other questions from online because there are actually 3,000 people. Join the room. And the first question is asking, the people are interested about the generative algorithm in material immerse design. They are asking if it's possible to combine this algorithm together with chemical automation. Then you can design. If it's possible, can you draw maybe more details to us?
It's a very challenging thing because the generative model is dreaming. It dreams compounds, and the compounds, therefore, are not necessarily synthesizable, and they are maybe sometimes crazy. So there is a beautiful paper by Yu-Song Jung from KAIST. I'm going to type it in the chat. Maybe people can see it. In Nature Communications last year, where he has generative models that only make molecules that are synthesizable by a synthetic procedure. So we want to collaborate with him in reducing his model only to the space of my robot, so that the model is constrained to only give you molecules that the robot can make. And that is a marriage, which I've been seeking for many years, as the people are asking, between robotics and generative models. And you notice that my project does not use generative models, uses a forward synthesis scheme, the laser project that we're doing. But obviously later, generative models will become imagining lasers that the robot can make. and that will happen by technologies like USONG. So retrosynthesis, forward synthesis models that generatively give you molecules that are synthesizable always. So imagine molecules, but all of them are only synthesizable with the procedures that you gave it. So that is the way I imagine they can be married. And obviously, with 3,000 people in the audience, there must be, 3,000 squared ideas about how to do it that we haven't discussed.
Mm-hmm. Okay, thank you. Then another question is coming, and it's about the database construction. Someone is asking if how to construct our own database from from other people's work. How to do that?
Yeah, you know what? I'm going to be very controversial, Jun.
Yeah.
Sometimes I think that you have to eat your own dog food, as we say.
Yeah.
You need to generate your own data because it's so specialized. Like my laser data is so specialized to my robot, to my conditions, that will be I will of course publish it, but it will be very hard for many people to generalize it or to another domain. But obviously, I wrote in some of the challenges that I said there that eventually, yes, all of these databases have to be available. I'm going to tell you, and by the way, June, you should do it in your journal. So I guess you are editor-in-chief of a journal, right? Artificial Intelligence Chemistry. I'm editor-in-chief of Digital Discovery, which is the Royal Society of Chemistry version. In Digital Discovery, we have 3 reviewers, and one of it is a data reviewer.
Yeah.
And that data and code reviewer verifies that actually the data is there. So first step, please put all your data from your robots in the supplementary of your paper. Let's begin with that. So I made it a rule in my journal. You should make it a rule in your journal. Okay? And then from that, we can start making a community where all the data is available. I have a database called Molar that people can download. It's in GitHub that does some of this. And the code that we call Organize It, we're writing the paper for it. The code that you saw that organizes all the labs is also open source, and we'll release it soon. It's called Organize It, for organizing organic chemistry labs. So I think the only thing we can do is just release the data, try to read each other's. For example, just quickly, we have a project for an organic laser project. We are using a data set from, I forget what group, I think it's a group in Korea, that looked at all the OLED data experimentally. And we use that database to pre-train our models. So in other words, those databases are important. I do apologize, I don't remember the name of the authors of the database, but I feel that that's what we need to be doing, and we're baby steps.
Yeah. Thank you for the wonderful advice. And if we can collect data from journal, probably in the future, people can just download your data and start his own work without even reading a paper.
Exactly. So data set papers will be more and more important. We were joking that our self-driving lab will write the paper and submit it itself. So I want to call it a self-driving author.
Another question is from someone asking that how can you manage to do wonderful jobs in 2 cutting-edge fields, including quantum computing and also machine learning? This is really, I also want to know the answer.
Okay, I'm gonna tell you what I tell people, because I'm getting older. I'm 47, and I'm gonna have a Lana Spool Music 50 party one day. So I started thinking about what had made me successful this way. And I think one of the most important things is you have to have a research group where everybody has a voice. Has to be very democratic. So my group is very large because I run 2 groups. I run the quantum computing group and the machine learning group. So we're about 35 people. But I think the way I run it is a flat organization. So my friend Peter Lord calls it an anarchist collective. So an undergrad has ideas, amazing. A high school student has ideas, amazing. So I think it is a culture thing that I was able to build, maybe also from coming from Latin America, where we are collectivists and hippies and leftists. So I think it's a political thing in some sense. The lab cannot be done top down. The lab has to be, and also you have to accept as a PI that you don't know all the details. As many times as I was telling you in my talk, I was trying to compartmentalize how much I know because I don't know too much about all the details of the robotic arm. I just have the vision and I work with my people to actually implement it. So I just have to tell you that I work in those two spaces, but I don't know all the details about it. But what I think is cool, and you can send some students to visit my lab, is the culture that we have created can be replicated. And I think it's just a culture of respect and very multidisciplinary, multi-ethnic, multi-different groups, etc. So I think there's a lot of that and enthusiasm. And the last thing I would say, be fearless. Like, you want to think about the future, do it. So like the idea about the robot that is going to do cocktails came up with discussions with my two other colleagues. Says, wouldn't it be cool to have a robot that does chemistry? So we say, how much is a robot? $20,000. Okay, let's put it on this table and let's start. And I think that is something that we don't do very often as chemists. We just are not adventurous enough. So my advice for all the young people in the audience, because I'm getting old here, but will be to just do that, to actually just be fearless and think about virtual reality or all the crazy things. So the crazier thing that you do, the better. So that's my advice. So there's nothing special about me. It's just perhaps the culture of my lab.
Mm-hmm. Yeah. Okay. Yeah. Actually, there are several other questions, but because of the time limitation, I will collect them and then send you emails, and probably then I can post the answers back. Yeah.
Okay, I'll do my best to answer as many as I can. June, thank you very much for inviting me, and I'm looking forward to seeing some of the rest of these talks. Thank you.
Thank you, Professor Alan. Yeah. Okay, so yeah, let me introduce our next speaker, Professor Joe Bowman from the University of the Emory University. He is a member of the International Academy of Quantum Molecular Science. His research focuses on basic theory of chemical reactivities. Joe has also made distinguished contributions to many fields, including reduced dimensionality of quantum approaches for reaction rates, and also to the formation and application of self-consistent field approaches to molecular vibrations. Recently, Joe also has developed machine learning method and applied it to DFT-based potential energy surface to achieve accuracy at the CCSD level, which is really amazing and useful. And today we are going to welcome him to give a talk about delta machine learned potential energy surface and dynamics with SIM. Yeah, please, Joe, can you please share the screen?
Yes.
Yeah.
Okay, thank you. All right, before I get started, I need to, let me get this first slide up. But let me just say, Alain, we've heard Alain speak before. Truly a visionary in our field. This was an amazing talk. And I knew it was going to be a virtually impossible talk to follow, with the same vision and scope. So needless to say, this is going to be a more focused talk. I'll do my best to make it interesting for you all. And well, first I want to thank Jun enormously for putting this together and inviting me to participate. As you can see, I'm advertising this journal. Actually, the title of this forum, I guess, is named after this journal, Artificial Intelligence Chemistry. You've already heard a little bit about it, so I don't want to belabor it. I just want to thank Jun again for organizing. I'm looking forward enormously to what happens in this journal. He's already corralled me and a couple of other people to co-edit a special issue of this journal, and we're looking forward to doing that, and some of you will be asked to contribute. Okay, let's see, click. All right. There's a way for me to get rid of this hide video panel. Is that going to do it? Okay. Well, we've heard quite a bit already. What is artificial intelligence? This is stolen from this website. And is artificial intelligence the same as machine learning? Well, who knows? Who cares? All right. What I'd like to share with you. So I do teach a course to undergraduates, and I hope Alana is doing this as well, finds time to teach. So I am teaching a course right now on machine learning to chemistry students, and these are seniors. This is one of the very first videos that I like to show them. Let's see if I get this to play for us. Basics of machine learning. We're not going to watch all of this, I promise. Let me just see if I can get this to run. See, I'm just not as good as this is. Some people, hang on. Whoops. I see it's the same problem. I almost got it. Let's try it again. Let me go back here. Okay, let's watch it this way.
We know humans learn from their past experiences, and machines follow instructions given by humans. But what if?
Whoop. This worked perfectly in the 2 or 3 times I played it.
We know humans learn from their past experiences, and machines follow instructions given by humans. But what if humans can train the machines to learn from their past data and do what humans can do at much faster?
I'm sorry.
We know human light to soaring.
Let's do
This
it.
is of the song's tempo, genre, intensity, and the gender of voice. For simplicity, let's just use tempo and intensity for now. So here, tempo is on the x-axis, ranging from relaxed to fast, whereas intensity is on the y-axis, ranging from light to soaring. We see that Paul likes the song with fast tempo and soaring intensity, while he dislikes the song with relaxed tempo and light intensity. So now we know Paul's choices. Let's say Paul listens to a new song.
All right, enough of that. Let me get back here. So what we're looking at here, what we just saw there, very badly done, was an example of what we call classification. So Paul likes music. And let me just follow up on something Alon said about understanding. Paul likes music with a very fast tempo and doesn't really like music with a slower tempo. We know that by asking Paul which type he likes. We don't really have a theory, I don't believe, maybe the neuroscientists do, on why Paul likes music with fast tempo, or does not like music with lower tempo. Well, Paul's a teenager. We can call on our experiences, but if Paul came from Mars, if Paul came from another universe, we would have to just conduct the experiment and find out what's what to get this clustering. We have no theory. We don't need a theory to understand this. This is just totally empirical data for us. Now, this is a trivial example of a classification, and we saw some of that in that nice video. It divides very nicely in this case. All right. Well, we can go a little further. So the left we would call classification, everything below 50 in these units. It does not like everything above 50 in these units of tempo is alike. Well, we can do regression on that. Again, this is a little elementary, I know. We can just fit, with straight lines. This is the most elementary example of what we call regression. And in machine learning, we often make the dichotomy into classification or regression. I do that when I teach.
忘了今天是周末，没定闹钟，一觉睡到10点。
I'm sorry. Is somebody out there?
No problem. Please continue. Yeah, sorry. Yeah.
Okay, are we okay? Can I continue?
Yeah, please. Yeah.
All right. Very good. Okay, so again, let's take a look at regression. And this was what we just saw. Essentially, we started with a classification, and we do regression. This is just fitting data, right? And in the most elementary example, that's what machine learning is about. In 2 steps here, we've kind of divided this into classification, and then we did some trivial regression on each class. Well, we could be a little more sophisticated and actually not do classification. We could take the entire data set here, all right, now represented by the same open circle symbol, and fit it. Well, if we fit that to a straight line, it's not very good. You can just look at it until we're getting a very rough picture of the trend. It's kind of it's qualitatively right, but it's not very good. Well, we can do more, and you guys don't know how to do this stuff. We can just put more sophisticated curves through this data and get much better fits. All right, that's elementary regression. Let's go to chemistry now for just a moment and take what I would consider a completely opposite example. I'm leading us down to something here. These are the electronic energies of CO, and we don't need a quantum computer for this, but it's a tough little problem that was solved using state-of-the-art quantum chemical methods maybe 15 or 20 years ago. And we're just plotting the electronic energy of carbon monoxide versus the distance between carbon and oxygen. That's trivially shown here. Well, if I were, again, thinking about classification, I might say, gosh, this is the attractive, all these guys here are telling me something about attractive interactions, right? The force is the negative of the gradient, and these are all coming, this is attraction. So out here beyond about 2.2 angstroms, the interaction between carbon and oxygen is attractive. That's from physics, basically, once we know the potential. But then suddenly the interaction changes, and at shorter distances, the forces are repulsive, they're positive, and this is a classification problem. These are repulsive interactions, these are attractive interactions, and I can do the same thing I did before with regression. Let's just put 2 straight lines through. Well, okay, not great, and you're all thinking, what the hell are we doing here? I can just take that entire data set and fit it. And in fact, in chemistry, we certainly know various ways of fitting this. Now, this is a machine learning method. It's just a one-dimensional spline. You know, even before we knew something about something as sophisticated as a one-dimensional spline, we have what's called a Morse potential. I think most of you still know what that is. Not that this is a Morse potential, but I could fit these data beautifully with a Morse potential. So this is a very different, outlook in a sense, but I'm going to be a little provocative. To a data scientist, these sets of data, these are both just sets of data to be classified or fit using regression. Liking music depending on its tempo, or the electronic energy of carbon monoxide, that's just data. But to we chemists, there is a difference, isn't there? And we'll discuss this a little bit. The difference is, how did we get the data? I think in these 2 examples, the way we got the data from, in the first case, what I would say, I guess, is totally empirical. In other words, we just asked this guy, Paul, or whatever, from some moon of Jupiter, do you like this music? Yes or no? And we collect the data based on the tempo. Totally empirical. How did we get the data for the CO? Well, as everybody knows, we solved the electronic Schrodinger equation. And we all know we spent years studying the theory of the Schrodinger equation and what's behind that. Now, that's certainly true. All right, in any case, what about the fits? Well, they're in the end, we're back in the same world. We're doing linear fits, we're doing polynomial fits, or whatever. How are these fits done? What they're based on? So on. So the answer is, again, independent of where we got the data, is it's machine learning, in this case for regression. So in a sense, so the machine learning techniques that, we're now using and which Alon is using to great effect are essentially the same, aren't they? Whether the data are empirical or ab initio. And, there are some differences. We expect that the ab initio data have no random uncertainties, whereas empirical data generally does. What I mean by the last phrase is not necessarily the statistical errors in measuring. Well, I guess I do. I could ask this guy, Paul, on Monday to give me his reaction to music on the tempos and so forth. And he gives me a reaction to, say, 100 different tempos, and I collect the data. And then on Thursday, Paul didn't sleep too well. I can ask him again, right, to give me his likes or dislikes for the music based on the tempo. And guess what? He's going to give me different data, isn't he? And that's different. And this is a real challenge for, I guess, most of what's going on in the world of machine learning is our data isn't even reproducible necessarily. Is the solution of the Schrodinger equation, given basis and a given method, reproducible? Yes, it is. And there's some fundamental differences there that I think it's, well, at least I'd like to keep in mind, something I like to tell my students. Okay, so back to sort of the bedrocks here, data science and machine learning. Data, this always is we've already heard a little bit about this. This is premier. There's no more, we can't move in this field without data. And we had a little discussion at the end of Alon's talk about data. And this is a huge, huge topic as well as a problem in a sense. And I think we got a little bit on that. So, in fact, we wrote a perspective in JCP in 2022. I got sort of on this topic, and this is particularly on data sets that exist now for MLPs. This is called machine learning potentials. So there are a number of data sets out there on GitHub, and we looked at a couple of these, and these all need to be looked at critically whenever we start. Before we get, too far ahead of ourselves, we need to understand what the data are, what their limitations are, and so forth and so on. But anyway, let's not get too far digressed on that topic, but it's clearly number one. Okay, so we've got the data. And we pick a machine learning model, and to some extent it may depend on the data we've got. Whether we're going to do a neural net, or whether we're going to do Gaussian process regression, or whatever, that may be influenced by the data. Okay, and then what? Well, we have to decide on descriptors, and I think later on we're going to hear a lot about descriptors. And to us, elementary and to students, this would be called the inputs. All right, so this is the inputs to our model. And then, as you probably know, we do the standard protocol of training the model, and then we test the model. All right, so we train on perhaps a 3/4 or something like that of the data, and then we'll test on, say, the remaining 1/4, and then we might even test on out of what's called out of sample data. All this jargon that kind of gets repeated over and over again as we do any particular problem in machine learning. Well, okay, then we have to ask ourselves, are we happy with the results? Are we happy with the test results? Many of you know about this stuff. I don't know how many, know this or not, but this is kind of the protocol. Basically, is your method capable of predicting results that were not used to train them? And that's prediction. Okay, so this is not an easy protocol to follow. Now, Alon is just incredibly good at this, and he spared us all the details. Otherwise, we wouldn't have been able to hear nearly any of the things he was telling us. But the details here are excruciatingly important. And all of this, starting from the data all the way through the selection of the model, the descriptors, et cetera, depends really on the mutual interaction of the human and the machine. And of course, in different hands, the success will be different. So obviously, to some extent, if we're trying to understand organic synthesis, you would think it would help if you knew something about organic chemistry. Well, maybe not. You might know, you might, at least for the descriptors, you might need to know something about organic chemistry. Okay, so now let me get into a little more of what we're going to talk about, and that's sort of in the title. We're going to be talking indeed about potentials and force fields. I'm going to try and put these two together, all right, in the era of machine learning, and these are the people who are the most important collaborators in this work. And I'll just let you read a little bit about all of them there. We've written lots of papers together, so there's the six co-authors on an awful lot of these papers. Okay, so we're down into a rather specific area here, and it's not a niche area, I would say, but and we'll explain why are potentials so important. We'll get to that, of course, if that's not totally obvious. So yeah, we're fitting data sets of electronic energies and gradients, and we're trying to be very anally accurate here. So we're trying to generate these with whatever the current state-of-the-art gold standard is. And let's for the moment just call it couple cluster singles and doubles and perturbative triples. Or when the molecules just get too big, or we're trying to do water or something like that, protonated water, we just can't straightforwardly use this method. So then we get into what's called delta machine learning to try and approach this level. And then our most recent work is asked whether we can extend this delta machine learning idea, again, at the couple cluster level, to force fields. Okay. So where are we as theoretical chemists? I don't know if not everybody out there is a theoretical chemist. I am. And in this field of theoretical and, say, computational chemistry, what's the dream? And Alain knows this very well. In fact, quantum computing is trying to realize this dream, and that is to solve the time-dependent Schrödinger's equation. Everybody knows this. And let's just be a little general here and let the Hamiltonian, let H actually be a matrix operator. We're going to use sort of the Born-Oppenheimer approximation or the adiabatic approximation, but maybe we'll include the non-adiabatic couplings. So this, in fact, would be the whole thing. This would be the Hamiltonian spanning as many electronic states as we might find relevant. We would include the non-adiabatic couplings. That's a horrific problem, and we can't really solve it. It can't even be solved. It's almost virtually not solvable to this day. For the ground state, and for any particular excited state, let's just say for a single state, and for the moment, ignoring couplings, so I can write a simpler equation. We can. This is sort of the whole field in simulation. We've got the time-dependent Schrödinger equation on the left, or we have classical molecular dynamics on the right. Now, both of these are, easy. Well, the molecular dynamics, of course, in fact, is far more pervasive than the quantum solutions. But the classical MD really only works intellectually for a single electronic state. We really are struggling still, but I'm sure we'll hear from Oleg about that, how we can couple electronic states, quote unquote, classically. That is still a very tough problem, even conceptually. In any case, the Hamiltonian that shows up in both classical and the quantum, everyone I think knows this, is the sum of two terms, the kinetic energy and the potential. This is amazing. All right, it's true classically and quantum mechanically. Now, for any molecule of n atoms, the kinetic energy is the same. It's just a very simple expression, p squared over 2m. What differs from molecule to molecule. What makes molecules or materials all different, of course, is V. V is the potential, and it is what governs the nuclear motion. It's unique to a specific molecular system. It's where all the chemistry resides. And this is why the obsessive attention that's being paid to potentials in the machine learning world of computational chemistry. What's the story? Well, it's high dimensional. Let's just say we have n nuclei, each one with 3 degrees of freedom, and this thing is 3n dimensional. Well, Cartesian coordinates aren't necessarily the best ones to use because they don't have the invariances that we'd like to see in this potential. So we might use something like all the internuclear distances in the molecule, of which there are this many, not a small number, n times n minus 1 over 2. In any case, representing this V is the goal of much of computational chemistry related to dynamics and potentials and modeling using classical or quantum simulations. And what's going on here? Now we're looking at a high dimensional space, either 3n or n times n minus 1 over 2. This can get big. And we're trying to represent V by calculating, hopefully, just thousands of electronic energies and maybe hundreds of thousands of forces. And then we're going to make use of regression methods for machine learning. And this is what has really kind of exploded in this field in the past 15 years or so. A brief recap, just going very selectively through here. I would call polynomial regression, neural networks, Gaussian process regression, kernel ridge, fitting gradients only, atom-centered kinds of representations, global representations, many-body. This is a huge landscape. It's an extensive landscape within this field. I want to point out a couple of interesting papers here. Pavlo Dral and co-workers wrote a very nice paper in Chemical Sciences where they actually looked at like 9 different methods to fit potential surfaces that are currently used, or extensively used, and kind of took an overview of all of them and did some assessment of them as well. We've got another very important thing down in the level here of methods is we've got to start assessing them. How well do each of these work? Under what conditions would one choose one machine learning method over the other? A little more recently, we did a similar assessment of these methods, and this came out in 2022, and I'll show you a little bit more of some of the results there. Now, this is probably oversimplified, but we're talking for undergraduates, this is not a bad start. I'll just divide the world of machine learning methods into 2 categories. One method that actually fits data and then basically discards the data. In other words, once the data are fit with a model, you might just throw the data away because now your model is what you're going to use to do predictions. A linear least squares of a straight line through data is an example. Well, so is polynomial regression. Neural networks are essentially an example of this as well. Neural network regression is highly nonlinear in general. Now, there are other methods that you would actually call interpolation methods. In other words, they keep the data while they're doing their machine learning. And 2 examples of this are kernel ridge regression and Gaussian process regression. They keep the data and they have to sort of live with a matrix inverse in their methods. All of these methods, of course, have their own peculiarities. I want to take you a little bit through the work we do, which is simple in a sense. It's polynomial regression. And this is under the category of linear regression, although it's not linear with a straight line, it's linear in a way I'll explain in a minute. The difference, so this is just taking a V, the thing we're trying to fit, as a linear combination of polynomials. Very simple, very time-honored. The polynomials we're using have special properties. They're called permutationally invariant polynomials, and I'll just say very briefly in a slide or two what those are. There's very interesting mathematics to get into the details of what we mean by invariant polynomial theory. But okay, let's say we can get our hands on them. The tau would be all the inputs. So for example, whatever, the coordinates of the molecule, of each atom. And the C's are linear coefficients. Couldn't be simpler as far as a regression model. C are just unknown linear coefficients. We can obtain them using standard least squares method. We minimize the so-called cost, and it can be done in one shot. And it's also, the evaluation is extremely fast. All right, what about the data, energies? We can gradients, just gradients. I'll say a little bit more about the sampling methods that we use. So let me just give you this little cartoon about what I mean by invariance under permutation. And this actually is a trivial, looks like a pretty trivial problem. This is just formaldehyde, H2CO. And on the left, you're seeing this simple configuration. Here are the two hydrogens. Here's the carbon and the oxygen, let's say. Now permute the two hydrogens. And so we can do that. I've called this one H prime and that H. Of course, they have the same hydrogen atom. Commute them, I get this configuration, right? Well, what you'll see rather quickly is four internuclear distances changed under this permutation. Two are invariant under this permutation. The two are obviously the HH distance and the CO, they didn't change. All the four other distances changed, and this is how they mapped. Well, if I were to take the world's simplest expression, world's simplest kind of polynomial, it's called a multinomial, and here it is. Instead of using the internuclear distances as my descriptors, I'm using what's called these exponential variables. So I've transformed the internuclear distances into exponential quantities. Nice property here is these variables go to zero as any internuclear distance goes to infinity, which is sensible because as internuclear distances go to infinity, interactions go to zero, and that will happen sort of automatically because that variable y will go to zero. Okay, this is not invariant. Simple monomial is not going to be invariant with respect to this trivial example of a permutation. And so this potential will not be the same in general. We can make it invariant in a very trivial way by forming this linear combination of monomials. And now under this permutation, we've already said two distances are invariant. This would be the HH distance. This is the CO. That's already invariant. Fine. These are the four other distances. And by making that simple linear combination now this is invariant, guaranteed, will give you numerically the same value when you permute the two hydrogens. Well, this is a totally trivial example. I just want to say, by the way, formaldehyde, back to, one thing I think I want to mention is, learning new science along the way here. So actually formaldehyde had an interesting history in this branch of dynamics called roaming. Some of you have heard of this, some of you have not. A very unusual reaction path that occurs in the dissociation of formaldehyde to make H2 plus CO, which does not go through the conventional saddle point. We only discovered that by actually running dynamics on a potential of this form and watching what happened. And of course, we had to agree with experiment. Of course, experiments can't watch roaming. Experiments can just determine certain observables, and we look for theory to see how well we can reproduce the observables. And we can only reproduce the observables by discovering or including this interesting roaming path. In any case, our whole research in this area in the past 15 or 20 years has essentially been an extension of this idea of how to make polynomials invariant. Well, it's a very interesting field of mathematics called the polynomial invariant theory. Mathematicians love this sort of thing. And there's even computational software out there to get these polynomials And this is our first attempt with Bas Brahms, an applied mathematician, using something called Magma. This is software generated in, I think it's the Australian National University. Other software, Singular and so on, our homegrown stuff, monomial symmetrization, originally quite a while ago. And the more recent work, very important stuff, and I'll try and get to it if I can quickly. How does this work? Just quickly, let's just take one example of a molecule H5 plus, trivial little molecule, right? And let's just truncate this monomial to some total polynomial order. Let's say 8. That's not very big, all right? So we're going to try and fit lots and lots of electronic energies, maybe gradients, with this expansion in polynomials. Well, if I don't put in any symmetry, if I don't remember, if I didn't know about the permutational, the 5 factorial symmetry, it's huge. This little molecule of a total polynomial has 43, almost 44,000 terms in it. You know, almost game over practically. We can't really, this is the end of the story. If we use instead the permutation invariant polynomials, 580. And not only is that essentially trivial, we're guaranteed to have the 120 permutations absolutely correctly described. And in some molecules, that's very important. Okay. Well, can we take this to bigger molecules? The answer is yes. There are various ways of doing this. And I don't want to go through the details there, but this is the superweak molecule. But the first one we looked at was transmethyl acetamide. And we were able to show a method where we could fairly straightforwardly get a full dimensional potential for this little guy. And not so little, but challenging to computational chemists with 2-methyl rotors. I was going to say immediately, we did not do this problem with a couple cluster theory. Too big already. We had to do something else. Okay, so just to remind us, we're talking about a mathematical numerical approach representing large data sets of energies and possibly energies and gradients. And we looked at this in some detail with this very long-winded title in a recent JChemPhys. And these are the acronyms. There's no reason, I am certainly not going to go through this. Some of these are of the form of the ridge regression. Some of them are neural network methods. Here are neural networks. These are Gaussian process. These are so forth. It turns out, and for reasons we really do understand, these are all nonlinear methods. This, what we call our PIP method, is linear. We can achieve the same level of precision. This is a pretty small molecule. It's ethanol. That's what was shown. That was picked by Pavlo Drall in his detailed analysis, and we borrowed all of his analysis for these other methods. We just added our own. Anyway, this little polynomial regression method runs about 100, maybe even 1,000 times faster than these other methods. All right, how do we get data sets? Very quickly, we're sort of in control a little bit. It takes a lot of computer time, but everybody in this field is generating data in pretty much the same way. You're running what's called ab initio molecular dynamics. People have been doing ab initio molecular dynamics probably for 25 years, 30 years, 40 years. Running trajectories, seeing where they go, learning things, but in general, until recently, people just threw the trajectories away. What a waste! All right, you run all of this stuff, you get some answers, and then it's gone. All right. We now use this as a training method because now we save the data, we save the gradients, we save the energies, and we can now use these as inputs. Now, direct dynamics is only feasible with very fast methods like DFT. That's okay. It's realistic enough to give us very good data sets. And then we can take these data sets and do all kinds of things with them, like prune them down to the essentials if we can do that. to figure out which data we need and which data is kind of redundant is another important technical question in this field. What's good data? What's useless data? How do you decide? This is still not easy to figure out necessarily. And it's another subfield of this field is trying to figure out what data has the most information. Sometimes it's obvious, I guess. Redundant data is certainly obvious. And then in any case, our goal is to prune the data sets we might get from a very fast, inexpensive, but realistic method, and just those geometries or those configurations, those, if you will, those specific values of descriptors, run gold standard calculations. And hopefully we can do this with an order of magnitude or two smaller data than we generate, maybe a couple orders of magnitude smaller data sets. Okay, active learning. Okay, another area of how do we decide what kind of data to get? Where can we get the data we need? So, a short summary of where we are in this highly focused field. We've generated about 100 potentials so far. I would say a few other things. Polynomials, these permutationally invariant polynomials are actually used as input for neural network and Gaussian process regression potentials. And these are the acronyms there. We've used invariant polynomials to fit dipole moment surfaces. They've been shown to be used for polarizability tensors. Again, these things will have interesting properties under permutation. Dipole moment doesn't change. It's a vector. Its components should show certain invariance properties if I permute the same atoms. All right. Permutation invariant polynomials are used in many body representations. I'm not going to go into those really in detail. The so-called NB pole water potential is an example of that. There is a special issue of JChemPhys coming out pretty soon, strictly devoted to software to fit machine learning software to fit potentials. If it's 100%, but I don't know if it's 100%. Maybe it is. So we've got a paper actually just accepted with all the gory details of how to download and use our software to generate these fits. Okay, so just let's take a look at a couple of recent applications to this and see what we come up with. Then the time that remains, I'm going to talk about two specific problems. These are real chemical physics-y problems. One is delta machine learning potentials and an application to tunneling splittings in tropolone. Why do we care about that? All right, it's a good question. A couple of other applications I'm not going to mention. We've got descriptions now at the very highest level for protonated water clusters. And how many people are doing water potentials in the field? Gazillions. Water potentials are arguably the most important force field or potentials that we deal with in the non-biological world, I guess. We just have reported a new one, which is a many-body representation in which we go up to what's called the four-body interactions. And I'm not going to talk about that. Sort of a new direction comes back to force fields. So force fields are pervasive in materials modeling, in biomolecular modeling, you name it. If you're going to be running atomistic simulations, you're going to be using some kind of force field. And the question is, can you improve these force fields? Can you delta correct them? And we think we've illustrated, yes, you can. And I'm going to show you some results, again, back to water. Okay. All right, just to indicate, we can do molecules of this size, and other people can do molecules, but almost everybody who's doing molecules of this size is not using couple cluster. It's just too big. It's really depressing, but we just can't. So everybody's using something like DFT primarily. You'll see that used an awful lot in the literature, and it's fine. There's a lot of good, I mean, people wouldn't be using DFT if it didn't have a lot of reality to it. Obviously it does. If we want to go better, there are problems with DFT for really precise work. It seems, this is what we sort of focus on in my work. Is how precise can we get? Can we get close enough to actually say we're practically at the level of experiment quantitatively? All right, so we're gonna really take a look at tropolone here, and the interest is in this hydrogen atom transfer. Classic problem, probably best illustrated by the smaller version of malonaldehyde. Malonaldehyde has a special place in the chemical physics field, both in theory and experiment. It keeps showing up. It's the if you will quote proton transfer problem that everybody works on. This is a bigger one, much bigger. This is 15 atoms versus 9. All right. Well, okay. So what is delta machine learning to bring these potentials to the CCSDT level of theory? It's really not, it's pretty straightforward. We've applied it to these molecules already. It is super simple. It is the following. There's a correction. All right. If I have a fit.
We are probably in short of time, please.
Sorry?
We are probably in short of time. Yeah.
Okay. Looks to me like I'm not, well, yeah, I've got about 15 minutes.
40 minutes for talk and 10 minutes.
Oh, yeah, you're right. That's fine. Okay. Oh, yeah, you're right. All right. So we're going to be fitting a difference potential here, right? And that's easy to do provided things are not all that different between a couple cluster and DFT. And they're not. Quickly, differences are small. So our goal is to fit the differences accurately. We can do it. We've benchmarked it. And we're going to try and do it on tropolone. Now, what's the challenge for tropolone? A lot of experimental data on the tunneling, splittings, and the isotopic substitutions. A lot of literature in the chemical physics literature. We've come to some interesting points here. Everybody focuses on the saddle point. There's a barrier separating these two equivalent minima. We can ask the question, is that barrier actually relevant? Well, so we've generated a potential surface very recently for this, even though, quoting this softball quote from David Clary, for this system, 15 atoms, full dimensional treatment is prohibitively expensive. Well, we've done it, and we've collaborated with some really good groups, particularly Jeremy Richardson using his instanton method, ring polymer instanton method. And I just want to quickly show you a couple take-home lessons. This is the instanton path. This is a very rigorous approach to tunneling in molecules. And this is the path that the instanton takes. This is a sort of multi-dimensional least action path. This is the saddle point. Well, the path is pretty far from the saddle point, isn't it? Called a corner cutting path. I'm not going to go through it in any detail. But when you deuterate, you'll find a different path. And the path is actually closer to the saddle point. I don't want to go through the details. Let's talk about experiment. These are the experimental splittings. They're very small. This is a tough problem for us theorists to try and get right. Splittings are under a wave number here. And of course, the experimentalists have worked very hard to measure these. This is the parent. These are isotopomers. Basically, now we can not only reproduce the trends, but we can get we can really get quantitative agreement there. Well, that's cool. In the next couple minutes, let me just give you an equation here. How could we apply delta machine learning to force fields? So let me say, in just this slide, and I can probably stop here. So if we read the force field literature, we see there's an awful lot of work to go beyond simple pairwise interactions. We've got to include many-body interactions, and most of these are polarization effects. We worry about short-range interactions. These are the so-called exchange repulsion. And there we go. You know, we make a lot of compromises to get some of this done. Question is, can these force fields be brought to a higher level of theory using delta machine learning? And then here's the trivial equation. This is our let's call it our many-body force field. And these are going to be the corrections to it. And we're going to be correcting at the 2-body, 3-body, and potentially 4-body levels of interaction. These are the differences. These deltas, again, are differences. They're just the differences between whatever this force field tells me for what a 3-body interaction would be compared to, say, exact cluster 3-body interactions. And we get this, the answer is yes, it can be done. All right. And just quickly, this has come out. Some of this did come out in Digital Discovery. Others, let's see. Anyway, yeah, there's a lot. We can correct the water potential. There's a take-home lesson I want you to say. Force fields fail. If you want a take-home lesson, the place where you see the biggest correction to force fields is not in the long range, but it's in the short range, where the force fields are kind of out to lunch when it comes to the short-range exchange repulsion interactions. These are very important for getting structures, energetics, and so forth. The canonical water hexamers are an example. Okay, so indeed, we can do this. This is my last slide. This is unpublished work. Back to water. We're delta correcting a force field, a polarizable force field for water. It's quite good, called TTM3. And we can essentially bring this to a superb level of accuracy now, doing the usual canonical comparisons with things like the radial distribution function at room temperature. I think the thing we're most proud of is we've laid this comparison with the water density. This has been the holy grail of potentials that are not cooked up to get the density at all. The density is no input, and we're getting this density quite nicely, and looks like we're getting that maximum correct. Well, if this was a talk on water, I would be talking to you much more about that. Okay, so there's our progress. I'm running out of time. And yes, we can correct. There's a way to correct energies. It seems like a promising way now to correct force fields. We have a perspective on this. It just came out. And it's called Delta Machine Learned Potential Surfaces and Force Fields with these authors. And I, again, want to reiterate thanks to other collaborators, Francesco Evangelista, Sridhar Gardre, and Jeremy Richardson. Okay, so with that, I'm done. And thank you very much for your attention.
Thank you.
Yeah, let's see what I should do now. I should stop sharing the screen, right?
Yes, thank you, Professor Bowman, and very nice talk and excellent results. Okay, so now is the time for people to ask questions. Anyone from the audience? Okay, maybe I also start with the questions I collected from the boarding cast room. And the first question is very general. It is someone's asking. Sorry, because it's in Chinese, I had to translate to English. And someone is asking, it is, do you know how many journals related to the artificial intelligence chemistry? And if I want to start the research for artificial intelligence chemistry, do you have any suggestions for that? Yeah.
You know, that's a very good question. In fact, I was going to ask Alon that question. So I'm going to, seriously, I was going to ask Alon what he would advise students to study, to get into, to get into the field. even in a general way. Certainly, in this field I talked about, it's quite a bit. It's just a slice of AI. How do we learn this stuff? It's a good question. As I said, I'm teaching undergraduates for the second or third time. There were no textbooks that I know of for teaching our students this. Alan, what do you say? What would your advice be to students?
Andrew White from the University of Rochester has some course lecture notes, and also I think Joshua Schreier. The idea, Joel, is I can promise to the people that in our Acceleration Consortium website we should organize them. But I know Andrew White has some sort of a textbook, and so those are the kinds of things that I think you can start learning more in a systematic way, other than reading the papers. I think the question also mentioned the journals. I think there's the oldest one in this field. I think it's Machine Learning Science and Technology, MLST, started by Anatol von Lilienfeld. And then, of course, there's artificial intelligence chemistry, which is organizing this, and digital discovery, and what else? I think those are the three main places where you can learn a little bit more about this.
That's right. I think this is really the undergrads and the just beginning grad students. This is a lot. This is a lot to ask.
Yeah.
Right. Right. So, I guess we would say, you better learn Python. you figure out how to use some of these modern codes. Jupyter notebooks. My students all play around with Jupyter notebooks. They play with scikit-learn. Right? All that stuff. And
yeah,
we teach that in a course. And I think we're going to have to start. We as teachers, not necessarily as journal editors, but as professors who teach, even at the advanced undergraduate, we're going to have to start thinking more about how to put this stuff into our curriculum. Add it to the list of things to do.
Yeah. Yes. And here we have a question in the Zoom conference room, and Chen Kai is asking, dear Dr. Bowman, thanks for your nice presentation. And can we use large amount of low precision naval data for pre-training and then retrain it using small amount of high level data?
Yes, that's certainly called transfer learning, and it is a very powerful side of delta machine learning, and people are using that. And again, the philosophy is the same, so there better not be very big differences between the low-level data and the high-level data, right? Otherwise, none of these methods are really going to work, or they'll work, but they're not going to work efficiently. So the hope is the low level isn't bad, right? It's got to be good. It's got to be realistic. It can't be nonsense. Otherwise, you just can't do a simple, either the transfer learning or the delta correction. I think isn't really going to work.
Okay. Another question is that thank you for describing the protocol or the procedure for machine learning training. And as you described, including data preparation and pick ML model and decide the descriptors. And which step do you think is more challenging?
Ooh, that's a good question, and I'll let Alan also address this. I don't think you can go to first base without the data. There's just we're not in business, right? Without data, there's nothing to do. So certainly the data, as they listed it first, is the most important thing. Now data isn't data. What is data? What are data? Right? We could spend a lot of time, and we do probably, Alan and I, we probably spend more time getting the data than the rest of the problem put together. Once you're satisfied that you've got good data, it spans the space and so forth, right? Then you can have fun. And that is the most laborious, time-consuming part. Maybe I'm exaggerating that, Alana. I mean, getting that data is really what it's about.
Yeah, let me just add to Joel the way I tell my students.
Yes, yes.
This, as Joel says, no question about it, data. And as Joel told us, representation is next. So you have to think about what is the best representation. Permutational invariant representations with polynomials, for example, but it could be permutation invariant SOAP potentials and things like that. Whatever you're using, the representation is going to be the next biggest choice in the accuracy and the generalizability of your model. First, you have to have the data. Then you have to think about what is the smartest representation that contains the most physics and the most symmetries. And finally, the model. Unfortunately, and this is for the young students in the audience, the students care about the models because they see these computer science papers. For example, the diffusion models and the so-and-so models. So the students always come and say, I want to use this model. And we have to tell them in chemistry, is the data or data? Then is the representation. And finally, I tell them, I don't care about the model too much because most models will saturate, right? Most models will give you more or less the same answer. So that's how I like to say it. And I think completely mirroring what Joel is saying. This is for young students. Yeah.
Yeah. Totally agree. Yeah. That's why we should include database in our journal.
By the way, I do want a second. I did have we have a paper in Alain's journal, and I believe it's the first one with this concept of the third reviewer to look at data. Now, the first time you write such a paper, you think this is a pain in the ass. I've got to now satisfy another referee. But to take it seriously, it's critically important that this be done, and that somebody puts eyes on the data that you're submitting as supplementary. I mean, we are submitting supplementary material these days to the journals, or we're putting them on Zenodo or whatever, GitHub or whatever. But somebody has to put eyes on this data and see whether it's really going to be usable by others.
And yes, the other question is, do you think WASP-6, the machine learning force field simulation results in WASP-6 is reasonable and transferable?
Oh, you said VASP?
WASP-6, the program WASP, VASP.
VASP, goodness gracious. I barely know the program.
Okay.
This is really, isn't it not for periodic electronic structure calculations, solids with periodic properties? I don't know if there's a force field necessarily associated with VASP. I don't believe so. All right, maybe there's another acronym that applies to it. VASP is not a force field per se.
Okay, and because of time limitation, maybe I ask the last question. Although there's many, and when you calculate the force fields, what's the difference for the big molecules and the small molecules? I mean, is there any difference?
Yeah, there's a difference. So, if you talk about, force fields, and obviously if we're talking about force fields for biomolecules, these are difficult. And we know there have been 1,000-person years of effort on the force fields that go by the names we all know, CHARM, AMBER, OPLS. And we also know that there is a community in the machine learning field that would like to reinvent, maybe that's too strong a word, or rethink these force field concepts even for biomolecules. And again, I'll mention Anatol from Lillefeld. Other people are rethinking conceptually, how would you represent large biomolecule potentials, force fields, maybe Adrian Royford with Annie and so forth. So these are kind of fragmented, trying to put these large molecules together in sort of sensible fragmented, in fragments, in sensible ways to do that. Now, having said that, if you look at the force fields that are out there, they're amazingly simple and amazingly good at what they do. But they're pairwise interactions, basically. Partial charges, Leonard-Jones, harmonic springs, whatever. Where are the many body effects and so forth? Well, they're all buried in the effective parameters somehow that these have been optimized. We know there's some fundamental physics missing from these, and it would be an enormous effort, to kind of restart that. But it may be that's what has to be done.
Yes. Okay. Is because of the limitation, time limitation, so we have to stop here. And
Thank you.
As my colleagues just told me, they add all the people in three different broadcast channels. There are in total 20,000 people join us with these talks. And we really appreciate Professor Alan Aspro-Pluguzik and Professor Joe Bowman for the very amazing, excellent talks. And we also wish to have you visit us in China in the coming future.
We would love to, I'm sure. Yeah, we'd love to. Thank you.
Yeah, thank you. Yeah, and thank all the audience. Yeah. Okay, let's meet in the conference room at 1:50 in the afternoon. Yeah. See you. Yeah. Thank you. Thank you. Bye bye. Have a good night, Bowman.
Bye.
Yeah. Bye.
This afternoon's forum. Good afternoon, everyone, and good evening, Professor Oleg. About 20,000 audience participated in the first session this morning. In the first session, Professor Alan and Professor Zhu gave very interesting presentations on the topics of self-driving laboratories and machine learned potential energy surfaces, respectively. There will be 4 equally exciting presentations in the second session. The first speaker on this afternoon is Professor Oleg V. Pristo. Professor Oleg, are you ready?
Yeah, I'm ready. Let me share then the screen.
Please allow me to begin with an introduction to you. Oleg V. Pristo is a professor at the University of Southern California. Oleg is the executive editor of the Journal of Physical Chemistry Letters. His research focuses on non-adiabatic molecular dynamics and time-dependent density functional theory, as known TDDFT. He developed machine learning methods to describe excitation dynamics. Oleg has made distinguished contributions to aspects of semi-classical and quantum classical physics to excitation dynamics in condensed matter and biological systems. His research group focuses on the development of new theoretical models and computational tools aimed at understanding chemical reactivity and energy transfer at a molecular level in complex, condensed phase environments. Professor Oleg's topic is accelerating and analyzing AB initial quantum dynamics with machine learning. Professor Oleg, please start your presentation now. Thanks.
Yes. Thank you very much for the introduction and for the opportunity. I hope China is going to recover very soon and maybe people like me could visit again. I always have very good collaborations with many people from China. I will.
Welcome.
Yeah, thank you. Thank you so much. So I will talk about our main topic of research, which is modeling excited state dynamics in materials. But because this symposium is on machine learning, we'll discuss how we use machine learning in the last couple of years, very recently, to accelerate and for simulation, to make bigger simulations possible, and also to analyze results. So on the first slide, I'm showing you some examples of what we study, which I'm going to discuss. So the top left and right is metal halide perovskites, which are very popular materials but they're quite complex and they show very different time scales and length scales on which they evolve. And modeling this at the ab initio level is quite limited, and we already are able to see very interesting phenomena when we apply machine learning. And the example at the bottom is the 2D material, which I'll also discuss, and then there's the metallic particle, plasmonic particle. In this case also, we see some rare events that can play a very important role in excited state dynamics in plasma-driven processes that are hard to study ab initio, but much easier and more interesting to study with machine learning methods. So this is the outline of my talk. First, I'll have a couple of slides explaining what we do. So what we do, we developed a quite unique methodology that models excited state dynamics in various nanoscale materials. It combines two techniques. It combines what's known as non-adiabatic molecular dynamics, which comes more from the chemistry community, and then it combines real-time TD-DFT that comes more from the physics community. And we use those two techniques because DFT is a very good way to describe electronic structure, as everybody in this audience knows. Non-adiabatic molecular dynamics is a way to couple electronic evolution to vibrational evolution. Then I will talk about 4 different ways we can apply machine learning to what we do, excited state dynamics. So the easiest one that many people are doing now, we develop machine learning force fields. These are quite important for materials that I showed you. For perovskite, for example, you can have some defect, vacancy migrating, or you can have an atom in this plasmonic particle that moves around. When that happens, different electronic structure arises, and then different excited state dynamics happens. But these processes take a long time. It's hard to do this by pure ab initio DFT. But our goal is not just to do molecular dynamics. So besides the standard way to develop force fields, which many people in my group are now developing, we also developed other tools. First of all, to be able to model excited state dynamics, we need to compute this full Hamiltonian, not just energy levels of the ground state, but also energy levels of excited state, and the coupling between electronic states. So this is the next topic. Alternatively, what we do now, and this is very new, based on some work actually coming from China, people develop machine learning force fields routinely now using machine learning. But now there's many papers that are using machine learning to train Hamiltonians. So they use ab initio DFT, and then they train semi-empirical, I would say, DFT. And this way, you can extend system size quite considerably. And have a very good postdoc from Xi'an, actually, who's doing this kind of development recently. The last topic is analyzing. So because machine learning can analyze large amounts of data, and any kind of simulation produces lots of data, we use some simple machine learning tools that can be used to analyze the results of our simulations. This can be done at a very basic level. We had undergraduate students from Singapore, from some other universities in the US, from India, that are supervised for their master's thesis, for example, using this kind of analysis. So what we do, it's called non-adiabatic molecular dynamics. Molecular dynamics is simple. You have classical atoms and then electrons that are quantum mechanical. But non-adiabatic means that you also include excited states and transitions between excited states. The ground state molecular dynamics is very simple, but we need to do excited state properties and also coupling between states. Because this coupling, it's called non-adiabatic. Because we study materials, we do real-time TD-DFT. So what we do is solve time-dependent Cauchy equations. In this case, we have these orbitals, Cauchy orbitals that evolve in time. The evolution depends also on the external potential that comes from the atoms, from R. Then we use adiabatic Cauchy orbital bases, and this is something that we've introduced because other people solve time-dependent Cauchy equations maybe on a grid in some other ways. But we introduce this approach, we introduce this adiabatic Cauchy orbital basis as the basis to evolve the time-dependent orbitals. We have to compute this non-adiabatic coupling, which is the key property in our simulation because it causes transitions between electronic states. People that do real-time TD-DFT, they usually use techniques such as Ehrenfest approach. And I should emphasize that non-adiabatic molecular dynamics methods that I learned as a graduate student with Khalif, for example, as a postdoc as well, they're very important. because mean field, NFS method that many people use that do real-time TD-DFT, it gives sometimes in physical behavior. It's rigorous, you can derive it, but it fails in some situations. For example, when you have an atom that collides with the surface, and then, for example, the atom can stick if it dissipates energy to the surface, or it can scatter elastically. If you have a quantum mechanical atom, it will split. The wave packet for the atom will split. But a classical trajectory in the NFS method would be an average trajectory that's not very physical. And this is something that people like John Tully realized in the 60s or 70s. They introduced this idea of surface hopping. So that's the branching. But what was realized later, the coherence I was part of, was that this quantum classical model with NFS, this average coupling behavior, fails to describe equilibrium. It turns out that you cannot dissipate energy from electrons to vibrations, and this is very important in applications to solar energy materials and any material, because you have many degrees of freedom and you have equilibrium at the end, thermal equilibrium, but you cannot get to thermal equilibrium with NFS. Another important point is decoherence, which is a more subtle point, but because you have this wave packet, if you do a full description, this wave packet splits, but classical trajectory does not split, or even if it splits, like in surface hopping, you don't have a wave packet. You have some very important effects, such as the quantum Zener effect, which is known in optics, quantum optics, which changes rates, transition rates forever, very fast. So for example, what it means in the limit of very fast decoherence is that if you decide, measure in which state your system is, if you try to do it all the time, dynamics just stops completely. This is known as quantum Zener effect. But we did actually quite a lot of development of these kind of methods. Then we did a lot of implementation. Because we study nanoscale materials, we have large systems, and we use this Concham representation. Even a very small system like silicon quantum dot, 29 atoms and 25 states in valence and conduction bands. Already, if we want to do double excited states, there was a problem of multiple excitons. We have 100,000 states to consider. So we have some techniques to be able to do dynamics in very large basis sets. And then in Van Dijk, he developed some sparse matrix techniques and so on. He's in Kyoto. Also, more recently, we started to do materials in which Coulomb effects are very important. Maybe for perovskite, it's not so important, or for metals, but for 2D materials are very important. And then you have this Auger-like process scattering, electron-electron scattering events. And we compute Coulomb matrix elements the way people compute it in real time in linear response TD-DFT. But we don't solve this Cassida equation. We don't diagonalize the linear response matrix, because when we have 100,000 states, it's very expensive. But we can use those matrix elements as off-diagonal matrix elements. And then the evolution that we do, the time-dependent evolution that we do of this type, has non-adiabatic coupling and has Coulomb matrix elements as well. Maybe I skip this. I should say that we also introduced an important approximation, which allows us to treat large systems, increase time scales. What we realize is that in nanoscale materials, you have many electrons. If you excite just one electron, you don't really change the density very much, and therefore you don't need to update density. So the density that we evolve using real-time TD-DFT changes, but the functional itself will compute with respect to the ground state density, and this requires us to update the functional every maybe femtosecond, not attosecond, on which electronic density evolves. So this is the first approximation we make. Saves us quite a bit of DFT time, basically 1,000 times faster or 100 times faster maybe, because we don't have to do DFT of consistency every attosecond, only every femtosecond. Also, we often assume that ground and excited state trajectories are very similar. This is known as classical path approximation. This is true because in many systems, not always, but in many systems, what matters are fluctuations, thermal fluctuations, as I'll show you in some examples. If needed, sometimes we produce excited state trajectories using constrained DFT and so on. And this is just an example that I skipped that shows a comparison of linear response TD-DFT and Concham excitations. Basically, if you look at Concham and linear response for this quantum dot, they look the same. You cannot see any difference. Everything is driven by fluctuations due to temperature effect. And Alexei Akimov, who was a very good postdoc in my group, has this code, PICSIDE, and he continues to develop it So if you're interested in what we do, you should look up his website. He has PixSite 2 and also some general environment as well, Libra. So it allows us to compute all those interactions, electron vibrational, electron-electron, spin-orbit. We do all this in a non-perturbative way. Everything is configuration dependent, which is very important for perovskites or metallic particles that have some unusual configurations. We mostly use VASP, but it's also interfaced with quantum espresso, CP2K, binding DFT, and so on. And I wrote this semi-popular science review of the methodology just recently. Okay, so now let's talk about machine learning. The first part is quite standard. We just developed machine learning force fields, but I'll give you important examples why this is important in nanoscale materials. So this first example shows you a metallic particle, gold pyramid, actually platinum pyramid, on a 2D material. And then what we model is we developed a force field with some SAIDI at that time. And we saw that on the time scale, this is the time scale of maybe 100 or 50 picoseconds, the top atom, it fluctuates. And it fluctuates, and when it does so, it creates some special state that is not very coupled to the rest of the system. So what we see is that when we inject an electron from the conduction band of the 2D material into this gold particle or platinum particle, we see this state populated immediately because it's right at the band edge. When it's populated, it has a lifetime of about 600 femtoseconds, which is maybe not too long, but actually making the time scale go from 200 to 600 can make a big difference because we're talking about some plasmon-driven chemistry, and bond breaking, oscillation of bonds happen maybe 50 femtosecond time scale, depends on the bond, from maybe 10 femtoseconds to maybe 300, 400 femtoseconds. So when we cross the bond length oscillation, and instead of half a period or 1 period, we can do 2-3 periods, this can actually improve plasmon-driven chemistry a lot. So this could be quite important. And this is only possible, I guess we could have done 250 picosecond MD ab initio, but it's quite expensive, so machine learning force field helps quite a bit. So now I'll mostly talk about perovskites, and this is work by Wei Li, I think he's in the audience, who was visiting my group for quite some time. He's now in Hunan. What he's done, he's modeled the influence of a very typical defect. In this case, you have extra iodine, extra halide, on the lifetime of charge carriers. So first of all, perovskites are very, very interesting materials, not because they are very popular and efficient and many papers are published about them, but also because they combine properties of inorganic matter, organic matter, and even liquid matter. So they have inorganic lattice, this octahedra, this green stuff with blue dots. And that's what conducts charges. Because of this, they're very good conductors of charges, very long diffusion lengths and so on. But they have inorganic molecule in the middle. Sometimes this could be organic molecule. Sometimes this could be inorganic cation, but often it's organic molecule, and people change the molecule and they could get 2D materials, quantum dots. Depending on how they choose the molecule, they can change the properties a lot. But so this is organic matter, but this molecule actually rotates and it has uneven charge distribution. So people like myself that come from studies of liquids at some point, even recently with ZhengZhou in Singapore, salvated electron, we actually talk about salvation because when you have a charge, this molecule can rotate, it can orient itself such that it screens the charge, and therefore you have charge-charge interactions that are screened, and this is quite good because you don't have excitons, you don't have charge scattering that also helps the transport in this material. But what's really important is that the defects in this material, they don't really cause relaxation. They don't cause charge losses. And this is Wei's paper where he looked at the interstitial. What we saw is that there's a very fast trapping. So you have a hole that is trapped by this defect. In normal semiconductors, titanium dioxide or silicon or cadmium selenide, when a charge is trapped, it does not escape. It's trapped forever and then recombines. But what we find, first of all, trapped charge recombines with the free charge more slowly than the free charges. So actually, this recombination is very slow. But what's even more important is that the trapped charge can escape back. So it's trapped within 30 picoseconds, but within less than a nanosecond, it escapes. And at that time, we were very excited to see this, had a good paper. But more recently, we actually analyzed what's happening and why is this happening. We thought it's because this is shallow and the coupling is very strong. But what we see more recently, we actually saw that before, but didn't really pay so much attention, is that we have this very large fluctuation of energy levels. So this is also interstitial, but in a different perovskite, but very similar. You have this energy level that in a static picture is just static, but it actually fluctuates up and down a lot. Sometimes it's shallow, sometimes it's deep. So in fact, you cannot even say if this defect is shallow and deep. So the whole terminology that people develop for traditional semiconductors actually does not hold anymore, because you have this huge fluctuation, could be 0.1 eV or 0.001 eV close to the edge of the valence band, or could be almost 1 eV deep. Is it shallow or deep? And this happens with other defects as well. This time scale is still ab initio, but I'm going to show you time scales much slower, hundreds of picoseconds, where you have very deep fluctuations. I'll show you later. This is another example, collaboration with Limin Liu, now in Beihang University, and Chunjia Tong is also in Funan, I think, recently. And this is Wei Li. So you have this, now it's vacancy defect. You have missing iodine. In the optimized geometry, or if the vacancy is just in the stable configuration, it does not create any mid-gap states. But when this vacancy diffuses, it actually puts this trap state, the defect state, makes it a trap state, puts it inside the semiconductor. When this happens, you have a new pathway for recombination. And when this vacancy migrates, the rate of recombination changes by a factor of 10. So this could be quite important. This is another paper by Wei, emphasize again that these materials are very unusual. Even though they're inorganic, so you have inorganic lattice, lead iodide in this case, it responds very strongly to outside perturbations. So what happens in this case, you have the same vacancy, iodine vacancy, but now you start putting charges through the system like you have a solar cell or some optoelectronic device. And when you start charging this vacancy, you oxidize it. Initially, there is no mid-gap state. If you oxidize it once, you have one mid-gap state. If you oxidize it twice, you have two mid-gap states. The lifetime changes almost by a factor of 100. So not only equilibrium structure does not really give you any description of real room temperature situation, but you have to include realistic conditions. If you operate a solar cell, you have very different charge carrier lifetimes than if you have just sitting, your sample sitting by itself without any charges flowing. Okay, so this is the first example obtained using machine learning force field. Still, at this point, we developed this with the help of Wissam Saidi. And this is now 100 picosecond time scale. This is the same vacancy. And this vacancy, the optimized structure has no mid-gap, no trap states. When we do 5-10 picosecond of initial trajectory, also nothing major. So if you look at this first 10 picoseconds, maybe there was some drop. But then after maybe 20-30 picoseconds, we have a huge drop. And this happens maybe every 50 or every 100 or something, every 50 picoseconds. So what happens, you have a very slow oscillation, acoustic mode, very slow motion in this material. And then, so optimized structure in this case, actually the distance between the two LEDs is 6 angstroms. But then it can become shorter, and at some point becomes so short, and this happens every 500 picoseconds, maybe 50 picoseconds, that this excited state drops by 1 electron volt. That's a huge effect. It drops down by 1 electron volt. So this is a very good correlation with the distance. So LED distance, if it's larger, the trap is shallow. If it's deep, then it's if the distance is small, then the trap is deep. Basically, it's very similar to this situation, except in this case, when you charge the vacancy, you actually make lead-lead bond stable by charge. But this lead-lead bond can form and create defect states like these ones, even if you don't charge, just from fluctuations in neutral state. What we are showing recently is that this is quite interesting because it extends light absorption. So if you look at the region that you have deep state, it extends very far into red and infrared. So you have a trap state, defect state that extends light absorption. It's maybe not very intense, depends on how many defect states you have, but you can absorb light very far into red and infrared. What's important is that the charge that you generate by absorbing into the defect state here can escape because the defect state fluctuates up, and when it fluctuates up, the charge escapes. So there are strategies like this with the traditional semiconductors. People dope Ko2 to absorb invisible, but they have to put lots of dopants because charges cannot escape. So they have mid-gap bands, actually, dopant-induced bands, new bands. You have very high concentration of dopants. But in this case, intrinsic defects that happen in the material, they actually extend light absorption and create more charges, which also increases efficiency of solar cells because you can absorb at lower frequencies. So now this is work by a student of mine. He got his undergraduate in Beihang University, chemical engineering, Yifan Wu. And now he developed a force field, and he looks at the grain boundary, because actually grain boundary is a very important part of perovskite, and it's very complicated. And the time scales that people see could be very, very long. We only did 1.5 nanoseconds so far, and already see interesting things. First of all, so we introduce the grain boundary, and then it creates many mid-gap states. Then we relax. It creates non-mid-gap states. There's a little bit here, but basically all the gap states are healed. You have some kind of sparse region here where there is a boundary, but seems like everything is fine. But if we do calculation, this is 1.5 nanoseconds, and we sample energy levels every so often, maybe every 50 picoseconds, in force field and then ab initio analysis, we see that we have some trap states that drop. So the band gap that was very large, so what was it here, was more than 2 eV in this case. Now it's almost 1 eV, a little over 1 eV, maybe 1.2 eV. So we have these fluctuations of the grain boundary, and they're much more complicated than fluctuations I talked to you before, right? So this is very easy to understand. Let's come together. But in this case, who knows what can happen? So lots of interesting analysis is possible. You have these fluctuating defect levels that can create quite deep states. Then we looked at some in more detail in some areas, and this is not a different time scale. So this is basically, what is it, 100 femtoseconds, very, very short time. Yeah, maybe 1 picosecond. 1 picosecond. This is 1 picosecond. You also see fluctuation of defect levels, and I'm showing you 3 examples. Sometimes the gap is very small, less than 1 eV, but sometimes it's large, sometimes it's more than 1.5 eV, sometimes you have multiple trap states. You have this fluctuation going on, you have trap states, you have very small gaps, but still the perovskite solar cell works very well. Why? Because all these fluctuations happen for a very short time, then charges that maybe would be trapped here and recombine in a normal semiconductor. When this level goes up, they fluctuate out of the trap state and they keep moving. So very, very different properties from traditional semiconductors. What's also interesting is that, so now I have a simple example where there's just one electron trap. So this electron trap is not on the boundary. So the HOMO, which is the edge of the valence band, is actually on the boundary, but it's not a trap state, or it's very shallow. But the trap state that we see here, it's not right at the boundary, it's second layer, it's some boundary layer. And also charges are separated, which is good because they live longer if they're separated. This is another example where I have electron trap and hole trap. So this is hole trap here and electron trap here. It's really interesting that those trap states are not at the boundary. Boundary is sufficiently soft and sparse. There's enough space so that it can heal all the trap states. All the defect levels can heal quite well. But you have this jammed some boundary layer that's not perfect, but it's not as soft. It's not, cannot heal itself. So all those trap states that we see in this system, actually they show up in this sub-boundary layer, second layer away from the boundary. More recently, we have this longer, bigger system simulation where we analyzed a little in more detail what's happening with the motions. What we see is that you have, first of all, you create grain boundary. You have a 3 picosecond sliding, very, very fast sliding of grain boundary, which is easy to do ab initio. But then we have this oscillation for maybe 300 picoseconds. And then 300 picoseconds later, you have something happening. So you have some distortion that's happening that we're analyzing, and it causes actually additional trap states. What we also find is that if we put some interstitial defect, now we put a point defect at the grain boundary, you have some new motions. There's some tilting, all sorts of motions are possible, and this is only possible to do because we can have machine learning force fields and we can do pretty big systems on nanosecond timescales, something that's impossible by ab initio, and we find very interesting phenomena that's very important for perovskites and for metallic particles. The next topic, so this was the longest, I would say. The next topic is interpolating the Hamiltonian using machine learning, because we don't want to just do geometry. We want to do excited state dynamics. We need excited states, non-adiabatic coupling, and so on. So first of all, yeah, this is now collaboration with the, so this is Alex Tkachenko, who is one of the people that started to do machine learning. He's in Luxembourg, and this is Wei Bin Hao. Interesting, yeah, I never met him, but I supervised his master's project from Singapore, and then he did internship with Tkachenko and me, but he was in Tkachenko because visa is hard to get to US. And now he's a grad student in Switzerland. Anyway, so what he's done here, he took descriptors, right? So to build machine learning models, you need some descriptors. So what people use for force fields, and then he tried to develop models for this non-adiabatic Hamiltonian. And this was just simple perovskite inorganic cation here. What he realized is that you don't need such a complicated model that you need for force field. I should say that in our case, this non-adiabatic coupling is a scalar. It's just a number. So in principle, you have velocity and you have this vector of the coupling, but what we really need is this product. And the product is a number, which is much easier to predict than even a force field. Now people are trying to predict this vector, non-adiabatic coupling matrix vector. It's very, very hard. But predicting this product number is very easy. So what we showed, first of all, you don't even need all the information about all the atoms. You can take every third iodine, and you already have this non-adiabatic coupling and then get in a very good agreement with ab initio. What's kind of funny is that if you take cesium, and cesium has no contribution to the electronic properties, the HOMO comes from iodines, LUMO comes from leads. So but if you take cesium in the middle, he can actually predict this coupling very, very well, even though cesium does not contribute to the electronic properties. If he takes lead, actually it's the worst. The iodine is the best. Cesium, yeah, cesium actually is better than lead. And then he just used one feature instead of 18, like in the force field, he just used one feature, developed machine learning model of the Hamiltonian, and obtained very good agreement in calculation with the initial calculations. So this is one way. But what we also do, we interpolate. So this was an attempt to develop force field-like, descriptor-like models. But now we don't really care about atomistic origin of this coupling. What we want to do, we want to interpolate, right? So we have a long trajectory, and then every 64 femtoseconds, let's say, we compute ab initio properties, but we need them every femtosecond. So we need to interpolate in between. And machine learning really is interpolation, right? Whatever you train it on, it can interpolate between the points you trained, but it's very hard for it to predict points that it has not been trained on. So now we have a trajectory, and we take points between, and we interpolate using machine learning. Now, and this saves us 50 times computational cost, because instead of taking every femtosecond, we take point every 64. Then we can get, this is more complicated system because we have a trap state now. The trap state has these fluctuations, and the coupling can be large. It's a more challenging example, but we still get good model. We have good agreement with ab initio results, and we can go down to 2% of initial data, 50% saving. And we tried different models. First, we tried convolutional neural networks, then kernel-rich regression. Now we even do inverse Fourier transform, which is really simple. And more recently, we started to do more complicated problems. So this is now A. So instead of cesium, which is big organic flow cation, we have Fa that has hydrogens much faster. This is a little more challenging because there are fast motions. Now we're collaborating with Klaus Müller, who is another pioneer of machine learning, and they taught us how to use more complicated bidirectional long-short memory neural networks. And those, we can still do 64 femtosecond time steps, but now we can capture these fast oscillations that happen because we have light atoms. And now what's really important is that now we can actually do dynamics. So before we had this 200 picosecond trajectory, but we could not do quantum dynamics because we didn't have the non-adiabatic coupling. But now we do. Or when we had excited states, it was only every maybe 100 femtoseconds or so. Now we can interpolate, so we have the full Hamiltonian every femtosecond with the like 50 times cheaper calculation than ab initio. What we see in this case, so if we do calculation that we would use just first 10 picoseconds, like we would do ab initio, we have one lifetime. When we have rear event, it actually becomes much faster. Lifetime shortens quite a bit, not too much, but maybe a factor of 5 or something. But then when we do the full calculation, because this trap state just can escape from the trap state, then we this defect state is not very bad. So if it only had defect state that was deep all the time, it would be 5 times faster, 5 times shorter lifetime. But because it goes up and down and charges can escape, the lifetime only changes maybe 20%. So not a big deal. Actually, ab initio in this case gives a reasonable result, a little flow compared to full result. Yeah, and then we also showed that if you populate those trap states, charges escape much faster than they recombine. So you don't see any recombination to the ground state, but they escape into the conduction band very fast. And this is very useful in applications. So this is now very recent. We just started to do this. So now we're using techniques that people developed in Los Alamos. And this is in, I think, Peking University, actually, to use machine learning models of optimistic Hamiltonians. So this is the paper just came out last year. What they do, they did machine learning training of atomistic type Hamiltonians for materials. Many people do it for molecules, but we want materials, and they did it for materials. And they did not do this system. They did perfect MOS2, and they did graphene, and they could do more array patterns, stuff like that, very large systems, and nanotubes of those materials. But we're interested more in photophysics of defects. So we created a defect trained. We had to actually modify their model because some energy levels were noisy. Defect levels a little more hard to train than the perfect systems. So now we have a machine learning Hamiltonian that's maybe a factor of 10 cheaper, so we can do bigger system. And we also developed a way using their code, but we have to compute non-adiabatic coupling, right, which is our development. And we see how machine learning model represents non-adiabatic coupling. So the energy gaps are very good. Non-adiabatic coupling much more challenging, but still not bad. If you notice, this is EV and this is milli-EV. So this is a much smaller property to describe. I would say people that are interested in maybe radiation processes like Junjian, for example, right? If you want to study spectra, this is the kind of property, the kind of quality you can expect. It's not the matrix element, but for radiative transition, it's not bad. And then we, first of all, I want to point out. So in this case, we introduce a vacancy. It's a very common defect, one trap state. So it's MOS2 with vacancy, sulfur vacancy, which we actually studied before ab initio. So it creates 2 trap states here, and 1 trap state here. But if you do optimized structure, this trap state, it's not really a trap state, it's very delocalized, it's very close to valence band. So again, if you do optimized structure versus room temperature, you have very different physics, which comes later. So if you heat it up, now this trap state is no longer as coupled to valence band, and it's very localized, which actually means that the size dependence or defect density dependence is quite different, as I'll show you. So what we now have the data is now we can use different system sizes, right? So from 6 by 6, which is already fairly big ab initio, we can make it 9 times bigger, 18 by 18, quite much bigger, hard to do ab initio. We can do full dynamics, everything. What we see is interesting size dependence, which is trap state density dependence, which many people ask us about, but was impossible to do before, including referees. But now we can see how lifetime depends on the defect density. So it does not have a strong dependence. It has some dependence. This is log scale, maybe a factor of 2 or something, 3. What's interesting is that you have different kinds of transitions. So you have those bars. So this bar represents TBM to VBM, valence to conduction band, and you have very significant dependence. So this is lifetime of transition from TBM to VBM. There's a very strong size dependence. Then you have transition from TBM to trap, and then the some size dependence maybe not so strong. And then you have transitions between traps. And actually, these are the transitions that determine the total lifetime. in this case, because you have localized trap 1 and this is hole trap and localized electron traps. Localized states don't feel size. So as you increase the size by a factor of 9, this purple line, which determines the total blue dot, actually does not change much, exactly because you are recombining. Trapping is fast, but your combination of trapped hole and trapped electron is slow, and that's why there's no size dependence here. But if we had the combination of trapped electron with free hole, it would be this orange line, and then when you have orange line, well, it's this process actually, but if you have delocalized and localized, you would have a quite significant size dependence. So this sheds some light on the defect density dependence of area lifetime. And the last example, which actually is the first thing we started to do with machine learning, we use machine learning to analyze data. So this is based on, again, Wei-Li's calculations, no machine learning at this point, but what we found was quite interesting, quite unusual. Another example of why perovskites are so interesting. This experimental data, this and other experiments, that show that when you increase temperature, lifetime of charge carriers in perovskites grows. Very strange. If you take a molecule or lead selenide quantum dot or silicon quantum dot, you freeze it and it lives in the excited state very long time. You heat it up, lifetime becomes shorter. But in perovskites, it's the other way around. If you heat it up, let's say from 200 to 300, the lifetime increases. So very unusual, total opposite. And the way we explained it, this is also strange because when you look at this electron vibrational coupling, it's velocity. When velocity is large, coupling is stronger, so relaxation should be faster. But you increase temperature, and this coupling actually drops, even though the velocity grows. Why? Because this matrix element, this part, freezes. Why? Because these are very soft materials. So when you heat them up, they deform and they create some disorder. They still conduct well. States are still quite delocalized, but you can have an electron that's localized in one layer and hole localized in a different layer. Matrix element for coupling electron and hole decreases. So this matrix element decreases because there's some partial disorder that's introduced, and that explains why as you increase temperature, lifetime actually increases, not decreases. Quite surprising. But what we did later was to use machine learning, which is just mutual information, very, very simple measure of correlation, but it's much better. You cannot do this with just simple linear regression, for example. Mutual information gives you correlation between, that's not linear. That's the main thing, right? Machine learning is nonlinear fitting, essentially. So what we find is the following. We applied it to the same problem. So we confirmed the geometry is more important than motion. Basically, this matrix element is more important than this velocity, because what we do, we correlate non-algebraic coupling with different geometric features. So we have this angle, and then only motion, velocity. So angle, which is structure, dominates. Only later, lower information responds to motions. Another thing we observe is that this II angle, which is this angle, is the most important angle. People talk a lot about octahedral tilting and octahedral deformation. So this angle, lead, is octahedral tilting, and lead, it's like this one, it's deformation. Very important, but actually this angle, I, is the most important angle. It determines band gap, determines electron vibrational coupling. So people guessed right, so they thought this is most important, but you can actually find something that's even more important. What's also interesting is that you have this organic component here, which does not contribute to electronic properties. It's just there for structure, basically. But in fact, it does contribute to band gap. It correlates with the band gap, correlates with the electron vibrational coupling in this case. Why? Because when it moves, it actually influences the lattice by steric effects. Also, it influences wave functions, right? So this is a sensitive property. You have wave function, you have electron, and this ion has some charge distribution. So when it rotates, it totally changes the wave functions, actually. It can localize it in between wave functions. So that's why, starting from the second row, also quite significant, we see many contributions of motions and structures of structure of MA, rotation of MA, that contributes to this non-algebraic coupling, and this plays an important role in charge carrier dynamics. So this is the end of my talk. I just want to summarize. So what we do, we develop a unique methodology for non-adiabatic molecular dynamics. I would say that usually most people that do this kind of calculations either come from molecular science and chemistry, and then they do non-adiabatic MD, very high-level calculation of electronic properties, or people that come from physics, they come and do real-time TDDFT, but they don't bother too much with how they couple electron evolution to vibrational evolution, nuclear motions, which play important roles. Things like rates are maybe wrong if you don't include decoherence, or you don't have branching, you don't have equilibration, you don't populate ground state in the long time, and so on. So we developed a pretty unique methodology that not many people in the group, or only actually people that maybe came from my group or collaborated with me, like ZhengZhou in USTC in physics, initially, they do these kind of simulations. There are many, many experiments. Every department, right, has many people using lasers, and they use lasers on all sorts of materials. So this technique is the best way to model excited state dynamics. Palm probe laser experiments could be optical or now X-ray, electron lasers, etc. Because it does it atomistically and it makes as few approximations as possible. Okay, and then what we do, we now have a full, now it's more of a, although we implemented everything, but have a picture of what we want to do, but it's a complete picture now. First time I'm actually talking about this kind of complete picture. First of all, we use machine learning force fields to sample rare events, which are very important in nanoscale materials. Grain boundary, for example, in perovskite, completely dominated by slow motions. You can have plasmonic particles, all sorts of things can happen on nanoscale that's very slow. You cannot do it ab initio, but not necessarily always you need it, but in some cases you really need it. So now we have ways to interpolate electronic Hamiltonians. So we now can compute. So what we do, we compute. In this last example I showed you, we developed a machine learning force field. So we developed a machine learning force field. Then we use this machine learning model of atomic Hamiltonian. Then we computed not every femtosecond, but every 64 femtoseconds. And then we interpolate. So all these three techniques allows us to go to much larger scale and much longer times, nanoseconds easily now, and scale depends still on how well we can develop these tight binding like models, machine learning models of Hamiltonians, but we can now do 1,000 atoms fairly easily. And then we also use machine learning to analyze. I gave you one example, but there are other examples as well. And I think I need to stop. Thank you once again for the opportunity to present. Thank you so much. Yeah, okay.
Okay. Many thanks to Professor Oleg for his excellent presentation. Does anyone have questions?
Hello, Professor. Here is someone from the USTC. I have a question about your third part about the real events. My question is, I found that you only use 2% of data for training and use the interpolate for the remaining 98% of data. My question is, if an event not in the 2% of data, is this machine learning force field also work?
Yes. So for force field, we use standard ways that other people developed. We use actually program DeepMD, I think. So for the force field, we don't develop anything in terms of methods. We just use protocol, right? Like we trained based on ab initio data. We sampled at low temperature, high temperature, many configurations, tested, and then, yeah, we did this. So force field, we use standard protocols because many people do it, so we don't really want to compete. But what we do excited state dynamics, which not many people do. And in this case, yeah, we interpolate. So this is the example that we showed. So what we compute in this case, it has to be energy gap, right? So we have valence band maximum, conduction band minimum, and then we have this trap state. So we need energies of those states versus time, and also we need non-adiabatic coupling of those states versus time. That's what we use, what we do here. So we have every 50 or 64 femtoseconds, 64 for IFFT, and then we interpolate in between. Yeah, so, and we tried some other, but this is the lowest we could do to get reasonable results. If we do 1%, then still we get time scales, but there are some deviations showing up here. Yeah.
Okay, got it. Thank you.
Hello. Thanks for your nice presentations. This is Yuanhua at USTC. My supervisor is Professor ZhengZhou. I would like to ask you questions. So can we get excited state structures by NAMD simulation?
Yeah, so excited state structure is just electronic property, right? So it's possible to do force field excited state, just like for the ground state. We don't really do it at this point, but because the cost is the cost of excited state calculation. So the way we describe excited states, including ZhengZhou's group 2, and we have some joint papers, right? They use constrained DFT, or we use some, if you want to, like core hole excitation. So we use basically some DFT tricks to calculate excited states, because otherwise we can do, I guess, linear response DFT with small bases. In CPTK, I think you can do this. Yeah, so basically you can use normal ways to do force fields and you can train them for excited states. But the cost is now the cost of the excited state calculation, ab initio calculation.
Oh, thank you.
Yes, thank you for the question.
Like I have also a question. I think it's important for the ML force field to sample the rare events, and but normally we trust the ab initio results more than the empirical results. But here, do you mean that because the ab initio simulation somehow cannot touch the rare events, so maybe it is even better to try or to apply this machine learning force field now?
Yeah, because the time scales are nanoseconds in this example, so it's hard to do this ab initio. In fact, we want to have bigger system and longer time scale, really hard. There's always a problem, right? Because you don't train including rare events, or maybe not exactly the events that you model. So we actually did, so he's a very good postdoc. He developed very carefully the force field, and he checked, you know, if he sees something, some kind of distortion, something like sliding, something happening, then he retrains, or he double checks that the structures, new structures he gets, he computes them ab initio and makes sure that the energies are right. Yes, I have to be really careful, especially if you're getting events that are not possible, you know, not natural in your training set. Yeah, that's important. Also, you have to use some kind of chemical intuition maybe too, if you start getting, I don't know, 10 bonds to an atom or something. Yeah, so it's standard by now, but still state of the art. You need to have people know what they're doing. Yeah.
Yeah. And this is very important, you know, because almost all the chemical reactions or chemical process include these rare events, and could be very useful.
And in simple systems, people talk about transition state, but when you have events on the surface, like you're interested in catalysis, you have many possible transition states, right? Maybe.
Yeah.
And they all compete. And if you heat it up, the structure changes. So maybe ground state structures for transition states maybe are not really fully representative of what happens at room temperature. Especially, this is a very soft material. Lots of things can happen. Yeah. Also, if you have like single atom catalysis, like in the very first example I showed you, this one atom can actually go back and forth every 100 picoseconds. And then if it goes away, you have total different maybe catalysis.
Yeah. Thank you so much. Yeah.
Thank you for the question.
Okay.
Professor
Oleg.
Can I ask one question? Oh, okay. Okay, I'm very I can see from your report that the machine learning force field is very powerful, and well, we can simulate something that the system that is very large, and even in nanoscale, nanoseconds, the time scale. So and what's more important that we can find the real several real events. And my question is, can we use this powerful force field to simulate the whole progress of a reaction?
Right. I mean, any molecular dynamics is limited maybe to microseconds, right? Also, machine learning force fields could be expensive. Depends on which force field. There's the local descriptors, global descriptors, and we actually now moving more towards global with Tkachenko because we also need like non-linear coupling, which is a global feature. Right. So I think it depends on the time scale. So I think maybe microsecond is possible. What's the rate? 1 over, yeah. So basically, if your rate is microsecond, you can do it. If your rate is seconds, I don't think you can do it. But yeah, but I think there are computers that are dedicated to just doing MD, right? What was the computer that people used for protein folding very fast? And those did huge simulations on a seconds time scale. Yeah, should be possible, right? But I guess the challenge is, right, once you're seeing some chemical event, you probably need to make sure your force field is right, machine learning force field is right. You have to like add training sets when it's breaking. So you have to be careful about it, which basically you do if you raise temperature, right? If something happens 1 microsecond at room temperature and at 1000 Kelvin, it happens in nanosecond maybe, and then you can train force field at 1000 Kelvin and then use it for room temperature. Yeah. Mm-hmm.
Oh yes, I think it is a real event for reaction to happen. So it may not need so much long time, but important thing is that, like what you just said, you have to make sure that your force field is correct for these real events, right?
Right. So for example, I gave you one example. We didn't do any force field, anything, ab initio. So how did we get this rare event for migration? We basically started somewhere here at the transition state, essentially, and then we evolved forward and backward in time, and then we had a full trajectory. Yeah, so there's a way to sample transition states and dynamics around transition states without having to do very long simulations, yeah.
Okay, thank you. Thank you very much.
Right.
Okay, Professor Oleg, since the presentation was also live online, many of the online participants asked interesting questions, and we have selected one of them. The question is, does the machine learning actually needs more computational costs?
Then what? But I mean, yeah. But actually, right. So I actually visited a group of Alex Tkachenko, who develops force fields, right? And they really want to do very accurate force fields. Especially, they want to study packing of molecular crystals, which is important for a drug design because crystal packing is important, molecular packing. Yeah, so they have very complicated ways to do van der Waals interactions, much higher level than DFT. They actually also have, right, if we all use DFT, we use Grimmer van der Waals, but they have a better van der Waals, Tkachenko-Scheffler, TS, yeah, van der Waals. Anyway, so they want to have very accurate machine learning force field. And in that case, there was a student kind of half-jokingly saying that it's more expensive than DFT calculation. But it's not true because it's just some raw code that he wrote. So it depends on the model. If you use a local descriptor, it's very cheap. It's not as cheap as classical force field, but still it's local. You don't need many nearest neighbors to include, etc. Cutoff maybe 7 nanometers. Yeah, not so big. But if you have global descriptor, it's like Coulomb interaction. So you have interaction between all elements. So it scales as number of atoms squared. And there are other examples. So then it becomes very expensive with a large system size. So you have to know, again, what you're doing in terms of how you're developing force field. Depends on your need, yeah. So this is probably better asked of people that develop force fields. I'm just giving you my brief experience. Thank you.
Okay, thank you. For the sake of time, we would like to thank Professor Oleg again for his excellent presentation. Professor Jiang, you can turn your phone. Okay.
Okay. Yeah. Thank you, Fernando. Yeah. So
thank you so much.
Yeah. Thank you. Yeah. And because of the time difference, so our next talk is going to be at 3:30 So we still have 15 minutes left for the break.
Yeah.
It is not easy to organize an international conference online.
Yeah, have group meetings with people all over Europe, China, and US. Some people have to wake up 4 a.m. Yeah. That's challenging.
Okay.
Anyways, yeah, okay. Thank you so much.
Thank you. Thank you.
Yeah. Thank you.
Thank you. Thank you.
Yeah, maybe I'll see you in USTC this year.
Yeah,
Good
yeah,
luck with
yeah,
the
please.
COVID, everything. Yeah. Thank you so much.
Okay.
Okay. Bye.
Bye bye.
Goodbye.
各位老师同学好，我们可能因为时差的原因呢，所以我们可能还是3点半准时开始我们下一个 session， 因为这个我们下面3位报告人呢都是来自欧洲，而欧洲的话现在还是他们的那个凌晨这个清晨吧，很早，所以呢这个我们下一位报告人3点半是这个Fenil Masros 老师。他那边现在事实上还是在早上7点多啊，所以我们可能大家这个耐心等到那个8点半我们准时，而3点半是他们的早上8点半我们准时开始。
The second speaker on this afternoon is Professor Philip Masris. Professor Philip?
Yes, I'm here.
Can you hear me?
Yes.
Oh, okay. Please allow me to begin with an introduction to you, Professor Masris.
Please.
Philip Masris is a professor at the Institute of Chemical Research of Catalonia. He is the associate editor of ACS Catalysis. His research has focused on the design and application of the quantum mechanics, molecular mechanics, as known QM/MM methods to problems of practical interest, and the computational study of molecular systems containing transition metal atoms. Recently, Philip carried out much research work to apply artificial intelligence to the field of catalytic reaction. Professor Philip's topic is hidden descriptors, an artificial but intelligent approach to the selection of these descriptor sets. Professor Masris, please start your presentation now. I'm sorry, please finish your talk in 40 minutes, and
Yes.
we will have about 10 minutes for questions or comments. Okay.
Yes.
Please start your presentation now, Professor Masris.
Yes. Okay. Yeah. Thank you very much, Professor Cui Cheng, and also the
Okay.
organization of this conference. Yes. So if I go over time, so I'm now just turning out my vocal clock. But if I go over time, please don't hesitate to interrupt me. So I'm sure the questions will be more interesting than what I have to say. Okay. So this seems to be working.
Okay.
Now, okay, so let's see. Yes, so here I am. Okay, so this is the topic of my talk. So of course, good afternoon to all the attendees in China. Here we are in the morning. Now it's 8:30, and of course it's a Saturday. So, and this is the topic of my talk. And there's a little bit of discussion on the title. So it's hidden descriptors. So this is the main focus of my talk. And then the follow-up is an artificial but intelligent approach to the selection of descriptor sets. Okay, so here I wanted to use the words artificial and intelligence because that's the topic of this forum. And I have to admit that I'm not so convinced that what I'm talking about is about artificial intelligence. What I want, well, it's not specifically artificial intelligence, but it's on the side. So I think that it's important to make this nuance because I'm aware that, artificial intelligence is very fashionable. Now, a lot of people are talking about this. And in fact, there was this article, this piece on Chemical and Engineering News. Chemical and Engineering News is the journal for general audience from American Chemical Society, and where they already thought in 2019 they were wondering if machine learning was overhyped. Well, the result is that a lot of people are claiming to do machine learning, to do artificial intelligence, and I want to avoid making this mistake. Of course, you have seen this morning talks that were very focused on artificial intelligence, and you are going to see others this afternoon. This is not the case here, but still, I think that we have something to do in this concern, and that's what I'm going to tell you about. So, of course, the starting point for our approach for our entering this artificial intelligence topic is the existence of a lot of computer power. So my research has been focused mostly on computational homogeneous catalysis. So we work on homogeneous systems, transition metal systems, and we see how they participate, what are the mechanisms for the reactions, and that has been our main topic on research for many years. Now, we realize now that computers are much powerful, which means that calculations are faster. The calculation itself is no longer the bottleneck of our work, typical DFT calculations. But now we have a lot of data, and this also poses a challenge to process them. Of course, the concept of machine learning is not new. These are some, so the ideas, machine learning, all of this is connected. Data mining is also another important concept. Big data is connected to this. So all these words are connected to machine learning. And of course, this is not new. Here I had from one of my students made a little bit of publications prior to 2017. These are the most modern ones, 5 years ago, before the big explosion of this machine learning in computational chemistry. And we see here work by Bo and Carbo in Tarragona, near my institute. Also, of course, the work by Sigman in Utah, Natalie Fay in Bristol. There is also this work by Rob Payton, who is now in Colorado State, Vidar Jensen in Norway, etc., etc. A lot of people working on this field. And this was 5 years ago. Now, more recently, there has been a big explosion. But what I want to tell you, so, of course, there are a lot of brilliant researchers working in this field. And we thought that if we wanted to make an impact, we should make something different. And here is the way I view the role of descriptors in this field and why descriptors are important. So the usual concept in artificial intelligence is that we have a desired property that we want to describe. Desired property, which can be something like an interselectivity, like solubility, like the binding energy or something. There's something we want to describe. And then we have a set of descriptors. And descriptors are just mathematical objects. That we have these descriptors for a series of chemical species, and we want to find how these descriptors correlate with the desired property. So we want to find a formula here, a figure of merit here, mathematical terms, and how do we connect this to the desired property. And then from the descriptors, we can obtain the value of the desired property without necessity to do measurement or accurate DFT calculation. So then, just simple examples of properties. We might be interested on sigma donating ability or oxidation state. And a typical example of descriptors would be the energy of the highest occupied molecular orbital or the Mulliken charge. Then this is the concept of seeing how descriptors are important for artificial intelligence. And now let me focus on what I view as the usual approach. And that's what most people have been doing on it. And they focus on the correlation. So how from a fixed desired property, which of course we cannot choose, but also from fixed sets of descriptors, we can find how they correlate. This is through random forest, neural network, vector machine, whatever method we can solve. And this has been the main focus. Then there is a minor focus on the chemical species. So do we have enough data, or we have to find more data, more diverse, etc., but again, focus on correlation and minor focus on chemical species. And if we want to make a difference, then our idea is to try to make a difference on the descriptors. So instead of using a set of arbitrary descriptors, let's try to find a way to determine which are the good descriptors for the problem at hand. And that's why we want to put the focus of our research on these descriptors. We have defined statistical procedures to find these optical descriptors, and that's what we want to do. And that's what this presentation is going to be about today. So this is organized in 4 parts. First, I will talk about an example from our group on conventional descriptors, and then we will go to the hidden descriptors. So this example on conventional descriptors, this is a collaboration with the group of Pedro Pérez and in Spain, in Huelva, and Gregorio Asensio in Valencia, also in Spain. These are experimental groups. And we have been collaborating for a long time on the reactivity of alkanes. So we have found, and they have done experiments, we have done calculations on the activation of the CH bond of alkanes, which these metallocarbene complexes, and then this is very electrophilic, and it's able to cleave the CH bond and produce 1 carbon and 1 hydrogen bond. So if we have methane, this can produce methyl and hydrogen. If this is a longer alkane, this can produce this longer alkane and hydrogen. And so there are a lot of data on this. Then the novelty here, so we have studied this for a variety of systems, but in this case, they were able to study systematically a series of alkanes through competition experiments. They put methane and another alkane, and they were able to analyze through NMR the selectivity of the reaction, the amount of products they were able to obtain. And with this, so they had 14 alkanes and 29 CH bonds. So we have 29 data. Let's try if we can fit them to some descriptors and to know what would be the electrophilic ability of these CH bonds from the descriptors without the need to do the experiment. And then, and we were able to obtain this type of figures where there is a correlation between the predicted and experimental. Okay, then what bonds did we examine? And these are the ones that they had in the experiment. So these are methane, and then there is methane. So the ones that are in red are primary carbons, primary CH bonds. So, and of course there are different ones. So then we have propane, we have butane, etc. Then the ones in blue are secondary bonds. So secondary means that this carbon is attached to 2 other carbons. And there are also tertiary bonds when this carbon is attached to 3 other carbons. There are also cyclic systems where they have secondary bonds. And so there were experimental measures for these systems. And then the transition metal complexes they made were silver and with these ligands. So these are complicated trispirazoyl ligands, but of course, these are the systems that work. So this is not simple chemistry. So you need kind of sophisticated ligands to stabilize this metallocarbene. And with this experimental data, and then we made a formula which was the logarithm of the relative reactivity, so about the reaction time, the reaction rate, the relative reaction rate, and we put it as a function of this type of formula. And here there are some coefficients which we had to fit, and there are some descriptors which we found that were efficient. First descriptor is the degree of substitution on this carbon. If it has 1, 2, or 3 carbons attached, or 0. Then the number of carbons which are on each chain. So R1 chain, how many carbons? R2, 0 or more. R2 chain, how many carbons? R3 chain, how many carbons? Then another descriptor, which is the number of methyl groups in beta position. And then a last one, which is a stereo factor, which could be 1 or 0 for very large systems. So, you can say So this looks like a caprice. So why the beta methods and not gamma methods or whatever? Well, we tried with a variety of more than 40 possible descriptors, and we found that these are the ones that work. Of course, they are not linearly independent, so there could be some connection between these two first, but we settled that on this one. Then how this works then? So what are the descriptors, for instance, for this bond here in P3? So P3 is the carbon type is primary because it has only one carbon. The chain is 0 carbons here, 0 carbons here, and there are 3 carbons here, so then this coefficient is 3. There are no methyls in beta, and there is no steric effect because the system is quite small. And then with these descriptors, what we obtain is a prediction of the logarithm of this relative reactivity of 149, when experimental is 140. Then when we use a secondary carbon, then we have different numbers here, and we have that the experimental value change, and we are able to reproduce this change also for another primary carbon and another tertiary carbon. So then, what else is in this formula? So these were the values of the descriptors. Then there are also the values of the coefficients. These A and C values, which has to be introduced in the formula. And this, we obtain them from fitting, from mathematical fitting, least square fitting. And we saw that for the different, they had experimental different complexes. The ones that were with silver have similar coefficients. And so this is a table. It's nicer, it's more nice to see it in a figure. So, and here there are in red the experimental values and in blue the predicted ones by our calculation. So, of course, this nice agreement. Actually, this graphic tends to emphasize the good agreement. But the important thing here is that we see that the graphics for the 3 silver complexes are quite similar. They also had 3 other complexes. Well, yes. So this is, so there are other silver, this is another silver complex that behaves differently. But the ones that behave even more different are this complex with dirodium. We see that the shape is quite different. And this copper complex where the shape is also different. So then, the descriptors are characterizing the different CH bonds, the different electrophiles, but the coefficients are characterizing the different nucleophiles, which in this case are the metal complexes. So what have we done with this? A predictive tool for the nucleophilic reactivity of alkanes, a promising scheme to characterize the properties of electrophilic fragments, and also a nice example of correlation between experiment, calculation, and statistics. Okay, this was this paper, which was nicely published and has been well cited, that's okay. But then, towards the topic of descriptors. So why did we choose these particular descriptors? Well, purely trial and error. And are there other descriptors that were better? Yes, maybe. Maybe the ones that we didn't try. And then the common question is, can we use statistics to find out these optimal descriptors, which we can label as hidden descriptors? And that's what we will try, but not in this particular problem, but on another problem, which is the bonding on transition metal complexes. So this is a collaboration with 2 postdoctoral students in my group, Oyeru Kunz and Maria Bezora. And this was our, this is the starting of this work on hidden descriptors. And the topic that we chose was the bond dissociation energy in transition metal complexes. And in the end, what we are wondering is what are bond dissociation energies made out of, because this is far from trivial. This had been approached previously by several groups, in particular, Odi Lichtenstein had this work. In one of them, we also participated, Maria and me. And, well, we had here good correlations, but let me admit that here we work on rather limited systems. These were in on phenyl ligands with fluorine substituents. So there were different number of fluorines and we see correlations, but it's kind of limited set of compounds. There was also work by Alquist and Norskov and Felix Stut on this more recent, but again, a limited series of compounds. And what we wanted to try to analyze was what happens when we had very diverse systems. And very diverse in terms of ligands. So we tried monoionic ligands like halides, bromide, methyl, phenyl. We tried neutral ligands like water, like dihydrogen, like ammonia. And we also tried dianionic ligands like oxo or sulfide. We tried also pi acceptors like carbon monoxide. So we tried to use as diverse set of ligands as we could. And as transition metal complexes, we took a series of standard complexes and we took away one. For instance, gold 1 complexes with chloride and phosphine are well known. So we took away the chloride, then we have a monocationic gold complex. But we also had this iron tetracarbonyl that comes from iron pentacarbonyl. And we also had this trichloride, titanium trichloride, which is also cationic, comes from titanium tetrachloride. And we try to be diverse in terms of metal center, most of them transition metals. We also tried with indium. So we try to be diverse, and then we want to learn about these bonds here. So, of course, there are no experimental data for all the combinations, and that's why it's useful that we are computational chemists, because we can compute with our methods all the combinations between these metal fragments and these ligands and make this type of table. Of course, I do not expect you to see the numbers, but let me mention that the numbers go from a few kcal per mole to very large number, near 900 kcal per mole. Because, of course, they are very diverse, but we can build this with a standard method. In this case was with LEAP, with dispersion, but whatever. So the useful thing here is that we use the same method for all, and in this case, in this concern, this is a good way to have all of them on the same graph. And then let's analyze these numbers. And the way we used to analyze these numbers was something called singular value decomposition, SVD. And the idea of this method is we have this matrix here, the BDE matrix, which I showed you before, and we can split it into 3 different matrices. One of them that contains information on the metal, the metals which are the rows here, another one that contains information on the ligands, which are the columns, and another one which is diagonal and that contains so the weight of each contribution. Of course, this is closely related to principal component analysis, though it's not, but it's similarly related. Of course, this matrix has the same dimension as this one and as this one. And this means that we are having a problem, let's say, of 400. You have 20 rows and 20 columns. And we are converting it into a problem of 400 plus 400, 800 plus 40, 850. So this is not a big advantage because we are adding more numbers to the description. But the nice thing of this type of decompositions, like singular value decomposition or principal component analysis, is that the decomposition is hierarchical. Hierarchical means that we can reduce dimensions, we can cut rows and columns on these matrices, and have an approximate description of them. And this is the key. So, and then we're going to say that these reduced dimensions are what we call the hidden descriptors. Then, this is another way to present the same story. So we start with the BDEs, then we have the decomposition, we reduce dimension, and we have, through this matrix product, we can generate another estimated BDE. And then what we have to do is to compare the 2 matrices. If we can make a good reduction of dimensions and the system works, then we will have this that will give a good result. And then we can compare just by comparing the numbers if they are similar. Then, a priori, we don't know if this will work or not, but these are the results we have. So, of course, if the system, well, so this is the table. So we see here we have in solid, this is the weight of its descriptor. On red, this is the maximum error, and on green is the average error. So if we only use one descriptor, the average error is already 10, which is not bad, but the maximum error is 50, which is completely unacceptable. Then we see that this goes sharply down. So the approach is working. Then let me show you this graphic in table shape, which is not so nice, but we can get to the numbers. And we can see here is the number of descriptors that we are using. When we use one descriptor, maximum error is 49. Of course, when we use 22, because we have 23 numbers here, 23 values in our system, the value is 0, but what we want is to cut here. And then this is purely subjective. So we decide that up to 5, the things are going sharply down. And after 5, the reduction is much smaller. So this is arbitrary, but we see that this is reducing the error by half. And here this is reducing by 20%. And then let's cut here, 5 descriptors. Then this is a way to show it in a nicer way. So if we make this presentation of the predicted versus the DFT value, we can see that the agreement is very good, R square. Of course, this is a way to present the results in a nice way. So, well, so we are happy, but not that much. Then, just to go further into the details, how this works. So this means that for each metal fragment and each ligand, we have a vector. So if we want to know what is the binding energy on this system, which is a compound of palladium with cyanide, we look at the vector for the palladium fragment, and these are the 5 descriptors. 1, 2, 3, 4, 5. Then there is a vector for the cyanide, which we also have computed. And then we have the descriptor weights, which are the same for all the systems of metal ligands, which come also from our calculation. Then we have to take these numbers, the first 3 numbers on each vector here, the second 3 numbers, etc., etc. This is the weight from each descriptor to the binding energy. We see that the first descriptor is the heaviest one, 25, but still the final value is 34. So the other ones are also important. And this 34 is just 0.7 away from the DFT. So by using these vectors, we can really spare to have the DFT calculation. And we think that this is quite good, and this tells us that this approach is working. Then we can also expand it by adding new elements to the basis to the set. Ligands, new metal fragments. There's a formula. That's no problem. And what is key here is that we have found a method to go from the BDEs to the hidden descriptors. Then we submitted this paper for publication, but the reviewer said yes. So that looks nice, but you should give also some chemical interpretation. And to do this chemical interpretation, what we did was to look at the ligands, put on the ligand side because ligands is more intuitive. What are the ligands that have the highest value for the first descriptor, for the second descriptor, and these are the ones that have the lowest value. And we see, well, so oxo has a large value for the first descriptor, and hydrogen has a small value. So there seems to be something there. And then what we did is to see how these hidden descriptors correlated to a standard conventional descriptors. And just computing correlation between 2 vectors. And we used a large series of standard descriptors, in particular 666. And we saw which ones correlated best with each hidden descriptor. And for the first descriptor, we saw charge decomposition analysis on this complex with iron tetracarbonyl and the LUMO of the cation, etc. for ligands. So we attributed this to sigma donation. For the second one, we have pi effects, so pi total contribution, ligand pi donor contribution based on NBO. So this we see a good correlation. So we think that the second descriptor is pi effects. Third descriptor was more tricky. because the highest correlation was with the distance between metal atoms, between the metal atom and the ligand, which was kind of awkward. So we had to think a lot about this one. But then we looked at the ligand at the metal fragments, and we saw that the ones with the negative, with the lower values, were with a few ligands, and these ones had more ligands. So finally, we attributed to the cis influence. So we attribute this third descriptor to cis influence, which is not present in the first two. Then for the fourth one, we saw that this is a covalent. So there is a lot of covalent also from NBO analysis, natural bond orbital. So we think that this goes to the degree of covalency. And for the fifth one, we did not find any good correlation. So we decided it was maybe statistical noise, but we could not analyze any further. So here, this is a nice graphic to show how each descriptor, the first four descriptors, correlates with the corresponding, with the best conventional descriptor. And we see, well, that correlation is from 0.9, but between 0.8 and 0.9. So not so bad. And we could assign also a chemical meaning for each of the descriptors, which is good. Then, conclusion here, the hidden descriptors concept works, and we can assign a 5-component vector to each ligand and metal fragment and predict the bond energy from them. Then there is a bonus track here, which is this matrix BDAP. So let's suppose that you are an experimental chemist working on transition metals and transition metal complexes, and you want to know what are the descriptors for your compound. So then what we offer is that if you do 5 calculations of bond dissociation energies, you input this into this website, you copy that form here, and the program will tell you what are the 5 descriptors associated to this ligand. This is done for an emitter support. So for N heterocyclic carbene ligand, and these are the bonds, just clean. And in fact, what I'm going to tell you next is how we applied this to this to a particular set of ligands, which were N heterocyclic carbenes. So this was published actually last year with Lucia Moran, Jaime Rodriguez, and inside the group. And the ligands are these N heterocyclic carbenes. These are particular systems where there is a carbon here, which is a carbene. It has only 2 bonds, which are 2 nitrogens. And, well, so this is known to be a strong sigma donor and a weak pi acceptor, but we wanted to try to make this more quantitative. For this, we used a variety of 8 different N heterocyclic carbenes where we change substituents. Sometimes we put a nitrogen nearby, whatever. So the carbene is always, the bond is always made with the one in this point. And we also tried with a set of metal fragments, because what we wanted to know is what was the bond dissociation energy of these N heterocyclic carbenes in these metal complexes, and we made 5 calculations for 5 complexes, and here are the averages. And then we wanted to evaluate how these averages correlated with the conventional descriptors. And to our surprise, we saw that the agreement was quite bad. So this is the energy of the HOMO. In principle, should be responsible for sigma donation. Correlation was as poor as 0.13, very bad. And of course, it's obvious here from the graphic. Then we analyzed why was it going so well. The obvious problem is that the HOMO is not always representing fully the donation from the ligand to the metal. In fact, in a case here, it's swapped and the HOMO is away from the donation. So this means that this is not so good. Then we try to correct changing the labeling of the HOMO. Things got a little bit better, but still they are not optimal because there are some tails here, we just mix everything up. There are tails around the 5-member ring, which are large enough to disrupt this correlation. So we tried also other parameters from MBO theory, the energy of the lone pair, which can also be computed. Correlation was very poor. And then, so we proved that the trivial conventional descriptors do not work. Then let's try with the hidden descriptors. And we saw that the correlation of the hidden descriptor 1 with the bond dissociation energy is very high, 0.9. So the hidden descriptor, which only requires doing 5 calculations, works very well. Then the first hidden descriptor already gives a description of the total bond energy. Of course, we can also, we can see differences, qualitative differences between them. And in particular, so for some systems, there is not so much agreement, depending on if the method is electron deficient or electron rich. We could also compare with these systems which are not exactly NHC, but which are related, and which produce similar values. So donation. So the first descriptor is between 0.16 and 0.23. The second one is between minus 0.12 and minus 0.13. So they have similar effects. And then we could also compare it to phosphines. And in phosphines, we see something which is interesting, that back donation is more or less the same. So the pi effects are more or less the same than for NHCs, but donation is weaker for phosphines. And I think, well, there has been a lot of discussion on how to compare NHCs to phosphines, and this provides a straightforward comparison where it says NHCs are stronger sigma donating than phosphines, and this is on an equal setting because that's the difference. Okay, so summary from this part: hidden descriptors are useful parameters that provide information on the fundamental properties of the ligands. And then we intend to apply this to other sets of ligands because we think that it's a good method. And with BDA matrix up, we will try to expand this into the community of persons doing work on transition metal complexes. And then the last example, which is our more recent work on this field, is the extension to organic reactivity. So we have shown that we can reproduce bond dissociation energies. Now let's try something else. Let's try to reproduce reaction barriers. And for these reaction barriers, we used a simple organic reaction, which is the SN2 reaction. SN2 reaction is where we have an sp3 carbon, in this case with methyl, where there is a substituent, which is a good leaving group, which is a leaving group, and there is another fragment that comes in and replaces this leaving group goes out, and the entering group binds to the carbon. This is a well-known reaction in organic chemistry, and in fact, it's known to take place like this, where this is a flat arrangement of the methyl fragment, and there is an inversion. If this is prochiral, there will be an inversion here, but we are not interested in this. So this is a well-characterized reaction in organic chemistry, which has a path. Here I have some adducts in gray, because the reaction is known to operate in two possible ways. So one of them is where there is an adduct between the entering group and the fragment, and then goes to transition state and we go to the adduct. But of course, it can also be that this adduct is not stable enough in free energy, and we go directly to the transition state. This means that sometimes you have to compute the adduct, sometimes not, to find the transition state. For the systems we found, we saw that mostly there was no adduct, so we operated with the energy difference between the reactant and the transition state. Then this is the treatment that we used. Again, similar to this one, we designed a system with 529 reactions. How did we obtain this 529? Was by combining all these groups that we decided to consider. So entering groups and leaving groups were the same. And you see here fluorine, bromine, and all the way to cyanide. So, and then we used, so these were the entering groups, and they were the same living group, so this was the other. So here, instead of giving the numbers, I give you this color code. The larger numbers mean that, darker means that the barrier was higher. So it's clear that this is more or less vertical, column driven. So it means that the living group will be more important. And that's what we saw from our analysis. So we did the same hidden descriptor analysis as before with the singular value decomposition. And to our surprise, we see that only one descriptor was enough. So here is 0 descriptors where we just had the average. And we see that with one descriptor, the error was very small. And then the other descriptors are just minor corrections. So we stay with one descriptor. And these are, again, we try to correlate with the standard descriptors. To our surprise, we see that the HOMO does not correlate very well. Neither the HOMO of the entering group or the LUMO of the complex with the leading group. Neither these standard electronegativity parameters. In fact, the ones that correlate better are these ones here, which is one thermodynamic and one kinetic. And only one descriptor required. Then also important, these are not the same values correlating for the leaving group and the entering group. There is an asymmetry between them. We highlighted this in the original version of the manuscript we submitted. Then, to our surprise, the reviewer said, yeah, but this was to be expected. Okay, so we reformulated this a little bit. But anyway, we found it from the calculation. And for leaving groups, we find that the correlation corresponds to the thermodynamics of the process. And for the entering groups, it correlates with the geometrical parameter for the tensions. And, well, that's nice, and that's good. So, and with this, I will wrap up my talk, as I think I only have 2 minutes left. So first, I presented an example of conventional descriptors, then the hidden descriptors and the bonding to the TM transition metal complexes, which we use to describe hidden descriptors and introduce the concept, and then to apply this to a particular type of ligands, and to present to you our related extension to organic reactivity. Then, concluding remarks, we think that using better descriptors is important, and also this is a work in progress. Now, let's remind you that this is a slide that was before. The novelty that we want to introduce in this field is to focus on the descriptors, to be able to find better descriptors using statistics. Of course, we use this singular value decomposition. Maybe this is not, of course, this is not the only possible methods, and we are open to consider other methods that can lead to better descriptors. But I think it's important to bring some focus to these descriptors, and I think that this can be improved and allow a more efficient application of artificial intelligence. And with this, I acknowledge the funding from the usual suspects. And of course, I have to acknowledge people that have done the work. So here are the ones in boldface, Lucia Moran Gonzalez, who is now a graduate student in my group. And then also, so Maria Bezola. And with this, I finish my presentation. This was my alarm, which I have to turn down. So,
Okay.
Okay, thank you very much. And of course, I will follow up.
Okay. Professor Masseris, can you hear me?
Yes, please.
Okay, many thanks to Professor Filio for his excellent presentations. Does anyone have questions?
Okay, I have one. Yeah. It is very interesting to hear the idea of hidden descriptors. So do you think the idea is similar with the hidden parameters when we try to deduce an equation, formula? Sometimes we have hidden parameters. Yeah.
No. Of course, I mean, so hidden descriptors is just a fancy name that we found. So in the original versions, we were talking about descriptors, but we think hidden descriptors look nicer. Of course, whenever we try to solve an equation, so the unknown is hidden. So hidden is just a label, but the point is that we want to put an emphasis on the descriptors. So what is
Yeah.
the usual approach is to use all the descriptors available. We say, okay, so but maybe this is not enough. Maybe the good descriptors are not the standard ones. So you need to find a new one. So that's the idea.
And another question is that it seems the prediction for BDE are many focus on the equilibrium state, because your training set is based on the ground state of the molecule clusters. Do you think it's possible to extend or transfer them to the in-equilibrium state? Because during the reactions, the molecule, the boundings maybe change the distance, and then maybe we have another situation. Yeah, please.
Yes. So yes. So the possibilities are endless. So here we focused on the binding dissociation energy, and of course, so please notice also, even in binding dissociation energy. So I said that we try to be as diverse as possible, but we stay with systems which have a small steric effects, because we think steric effects are easy to reproduce, but they would also affect. And then, of course, we could also try for transition states. We could, so the possibilities are really endless. The problem is, so we need to put a focus somewhere and then try to analyze this. So the reason why we did not try reactivity with transition metal composites, which is our main topic of research, because the reactions are too diverse. So, so binding dissociation energy is a reaction where you take away one ligand, and this works also in chemistry. This would be a dissociative mechanism, but then sometimes when a new ligand comes in, it kicks out the first one, and then this would be dissociation reaction, this associative mechanism, which would require another set of parameters, and which would require also a different fitting, etc. There's also the question of the spin states. So here we always use the ground state, but you could also think about using different electronic states and see what happens. So the possibilities are almost endless. And so you have the time and the interest actually is doing something. So it takes some time to set it up, but then once you set it up, it should work. And then depending on the problem you are interested in. So that's our idea.
Okay, thank you. Very promising. Thank you.
Can I ask a question here?
Please.
Can you hear me?
Yes, yes.
Oh, yes. Yeah, my name is Xin Chen. I'm a staff scientist from Hefei JiShu. It's a company actually founded and headed by Professor ZhengZhou. We are very excited by your research. Actually, I really believe the idea of the hidden parameters will revolutionize the physical organic chemistry. Because I got my PhD actually in the physical organic chemistry, studying the SN2 reactions, talking about the nuclear felicities, just basically talking about what parameters or what kind of molecules have what kind of nuclear felicity. This is the central idea in physical organic chemistry. And when I first read your paper about half a year ago, I'm really excited because we actually tried something very similar. First, we actually repeated some work of your SN2 reactivity work. We actually found exactly what you follow your lead. We actually repeated your work a little bit, and we show that yes, you are right. You only need one parameter for the entering group and one parameter for the leaving group. You can describe the SN2 reactivities very well. But what we are interested in is in actually what happens on the central atom carbon. So what do we know that if we put a substitution on the carbon, it will significantly change the SN2 reactivity, which makes sense, right? Nuclear felicity means how much you like the nuclear, which is the carbon atom here. So we change the substitution on the carbon, it will definitely completely change the nuclear felicity. So we tried different substitutions like cyano, like CN, like all kinds of halides. What we found interesting is if we have no substitution, yes, you can actually use the SVD to separate the entering group and the leaving group. and perfectly with only one production, and you got all your need. But with substitution, we need two products. So we need not only one set of the hidden parameters, we need two sets of them. And the ratio between the contributions is always about 3:1. So this is something we are very excited and also confused about this. I just wonder if you have tried put the substitution or other similar effect to change the electron clouds on the carbon and see the similar effects.
No, well, so that's very interesting. So I don't know if the results are published, but I find it very exciting.
Yes,
of course, that's yes.
Yeah,
So,
without the too much detail, I guess we probably need some time. Maybe we would like to contact you after talk to actually share some results. We really would like you to give us.
Okay, that would be great. But then to address your question, yes, so your results are very interesting. That's also one of the directions where this could be expanded, but we did not consider it.
I see.
I can tell you another thing. What we have been working is in the reaction of electrophilic aromatic substitutions on phenyl rings. And well, so that's something also where there we have the entering group, and then we have a spectator substituents, which is also something interesting. And then we have at least two parameters. Then also about SN2, so I can tell you also something else. So in order to get closer to experiment, we sometimes have to add something binding to the leaving group. So because if you look at the experimental data, sometimes, yes, so you put an anion, but then depending on the leaving group, the anion also can, So the anion comes with a cation, and then this cation can also move to the leaving group. So then there's also an additional complication that has to be taken into account, that maybe the systems that we used here were too simplified. So sometimes you have to consider if you have, well, so if you want to compute how iodide replaces chloride, then you have to take into account that iodide will usually come with maybe potassium iodide, and then the potassium will move to the chloride side, and this will be the real barrier, etc. So, okay, but anyway, that's the nice thing. So that takes us to another way to explore the chemistry. And in the end, that's one of the goals here. So of course, we do not get necessarily better reproduction of results. So all these reactions, we could compute the barriers with DFT. That was one of the criticisms we got from nasty records.
Yeah.
But then what we want is to learn fundamental aspects about the chemistry. And what you just commented on your work, I find it very interesting, and I think that's the way to go.
I see. Very nice. Just one quick comment. I think the idea of you working the organic metalysis, which is basically your center atom is the transition metal. I think you can actually probably use the same idea about because you can think about this complex as ligand exchange reactions, and a lot of catalytic reactions actually based on the ligand exchange. So the one ligand binds to the metal center and it makes some change and leave. I think this is a huge opportunity here. Using the hidden parameters, we can probably make predictions of which kind of organic metalysis species will work as the best homogeneous catalysis. I think that's even bigger, probably have even more applications than just the physical, the physical organic chemistry itself. So I'm very looking forward to, whether you're gonna want to come up, and we'll probably.
We have to move for the next talk.
Okay, sure. Okay. Thank you very much.
Okay, for sake of time, we would like to thank Professor Masseris again for his exciting presentation. Okay, goodbye.
Okay, goodbye.
Professor Masseris.
Yes, I stopped sharing my screen.
Okay, the third speaker is Professor Lee Cronin. Professor Lee Cronin, can you hear me?
Yes, morning. Hello, just sharing my screen.
Okay.
Good morning.
Well, you can see my screen?
Yes, it's starting now, yeah. But not in the first screen mode. Takes a little bit time.
Okay.
Okay.
We can see your screen now.
Okay, fine.
Okay, Professor Li, are you ready? Please allow me to begin with an introduction to you, Professor Li. Li Cronin is a professor at the University of Glasgow. He is a designer and developer of computer and automatic synthesis robot. Li proposed and implemented the use of affordable modular chemical machine systems for the synthesis of important chemical molecules. His research is anchored by 4 key missions: exploration of assembly of artificial life in the lab, the digitalization of chemistry and self-assembly, elucidation of the fundamentals of information theory in chemistry, and the creation of a chemical computer. Professor Li's topic is universal chemical discovery and synthesis machines and computation. Professor Li, please start your presentation now. Okay.
So, hi everybody. It's pretty early here in Glasgow. You can hear me okay?
Yes.
Good. So I'm going to talk to you about the work that's going on in Glasgow, particularly around the area of computation. And computation is kind of an interesting word because it really means that computation does for chemistry what computation does for mathematics. So what does computation do for mathematics? Computation takes an algorithm and some data and produces a transformation on that data to some output. What computation is the transformation using an algorithm in a suitable hardware on input reagents to a well-defined set of reactions and material outcomes. And this is what I would say a kind of practical ontology relationship for doing chemistry, all of chemistry, not just organic chemistry, but all of chemistry and materials. And it's really important to have an ontology if we're going to use machine learning or artificial intelligence for materials discovery. And this is the first kind of attempt at that, which I started, I guess, probably 20 years ago now. But why did I start doing this? Well, one of the big reasons I want to build a synthesis engine for discovery is because I'm interested in discovering more complex systems, origin of life. But what becomes quite clear in chemistry and material science that there are some big problems. And these problems are listed here on this slide here, that the processes to make stuff is not reproducible. You know, take any molecule, battery material, you have to read the paper, you have to understand the experimental, you have to then try and implement that in your laboratory with your research students and hope that it works. And if it doesn't work, why? Is it because the paper was bad? Your reagents were bad? Your students didn't understand? You know, it's really, there's lots of places where it can go wrong. Whereas if you take in the area of computer science, if you take some code from GitHub and you then basically install the right programming environments and the dependencies, the code should run on any hardware. So reproducibility is one problem, but actually not a big problem. What's bigger problem is that discovery is expensive and time consuming. And also in chemistry and material science, there's no reward for collaboration. There's lots of fierce competition. No one wants to really share their secret material or their molecule or their synthesis. They want to basically publish it first and then move on to the next thing. And PIs are rewarded for prestige papers, not reproducibility.
being first is more important than standardization, and there's no digital hardware standard, and platforms that do exist are very expensive. Now, that's going to change, and that's what I'm probably trying to do. And that's why I'm here today and very excited to kind of explain to you what's going on. So why is this needed? Well, we need to move away from the kind of balkanized research and reporting mode, and we need to move instead to a model of software industry which is proven and scalable. That means we want to have every chemist have access to this. You know, chemistry should be a science, and arguably is a science. Well, certainly I do science in chemistry, but lots of people are not doing chemical science anymore. What they're doing is something a little bit different, and we want to kind of get people back to doing science and at the cutting edge of knowledge. And so one of the things we want to do this is to have this kind of the standardization, and then catalyze acceleration from a universal software standard and vast shared data to kind of have like a GitHub for chemistry. So one of the things we've been doing, I guess, is to invent the concept of digital chemistry, which I invented about 15 years ago. And really the concept is, can we use a hardware standard, a code standard, and convert the code into molecules? And so you should view this as the attempt of making a kind of Python for matter. So the computer, the concept, computers do computation, is the Python of matter. And to do this, we need a programming language, which we call ChemDL. And ChemDL is a representation of the process algebra and the chemical engineering and the chemistry for both making, manufacturing, and most importantly for me, discovery and understanding. And the idea is to go from molecules to code and code to molecule. And so we're kind of making a ChemMat, if you like, which is a GitHub for materials science and chemistry. And it's not just molecules, but materials and devices and composites. Obviously, it gets harder the more complicated the material, the more complicated the device. And actually, a very nice place to start is in the synthesis of organic and inorganic molecules. What we've been doing to kind of make this a reality is creating a standard for software and hardware, which is, you should view a bit like the standard for digital computation, which is, you know, right now, the way that digital computers work, there is a processor that has a programming has a microcode, and there is obviously an architecture, the processor, the memory, the input and outputs, and so on. So what we needed to do is kind of understand how to build the standard hardware that was cheap and modular, and then also build a programming language. And this simply isn't just a question of solving chemical engineering. It's about building an entirely new ontology and mathematical structure, almost for contracting this work. So the standard hardware contains operations universal parameters, which I'll explain. And although it sounds really basic, right? So, you know, chemistry is about adding reagents, mixing them, stirring them, potentially heating them or cooling them. But we've got to kind of do that in a programmatic way on demand. And what we've done in my lab is build all these modules, and I'll explain them. Like on the left-hand side here, this module is a digital manifold for vacuum and gas. There's a Schlenk line here for control for very high the air-sensitive materials. There's a portable robot, which you can take anywhere. There's portable purification, kinetic analysis, so we can do automated and controlled mechanistic work, and so on and so forth. And so the aim is to build on a modular, universal, and scalable, and most importantly, teachable. The students need to understand computer systems and make an open standard for robotics. Think of it like quick fit glassware for robotics and chemistry. And we need to make sure that we can then integrate existing hardware that is made by some companies and very expensive. So it's very possible to buy lots of very fancy robots and put them together and do things like on a production line, but it's not possible to share that code with other labs around the world to be able to copy you. That's not possible. So we're going to try and kind of explain how we need to make that possible. First of all, we need to think about the abstraction. Now, organic chemists have been building abstractions for years, but I'll explain why in organic chemistry and mechanistic chemistry and theory, there are kind of three different abstractions. So there's the theoretical abstraction of chemistry based upon quantum mechanics and understanding how to represent bonding. There is the practical abstraction of organic chemistry to think about the functional group interconversions. And then there is the abstraction that is associated with understanding the mechanism of using electron density and ascribing bonds, leaving groups. And these need to be combined together in some practical way. And if we just take software as one example of how this abstraction works, you take at the top here, in the software domain, you have applications and programming languages, and then libraries and operating systems. So that's very high level, all code. Then on the digital domain, on which the software domain rests, has a computer architecture components, integrated circuits and logic gates. And then the physical domain, where everything is done on the transistors. And so you need to kind of think about how are we going to do this in chemistry? Where are the transistors? Where is the digital domain for interfacing the software domain so we can then make the chemistry universal? This, for chemists, this is quite hard to understand because computer scientists have been working on this now for 70 years. And the concept of a Turing machine, which is a universal system for chemical discovery, Turing machine, which is a system for universal computation, is not being implemented in chemistry. As I said, abstractions already exist in chemistry. We have a retrosynthetic analysis for reaction planning, and obviously in this case you take the target, disconnect the targets, produce a series of steps that you think can then go into produce the target on paper, and then put in some plausible reaction conditions, and then you go into the laboratory and you try it. And so what that means is that you use the abstraction of retrosynthetic analysis to produce a route on paper that may work, but you have to manually go in the laboratory. So there is no physical instantiation of a way of programming this without having to do it first. And to be honest with you, organic chemists have done this kind of on purpose to keep themselves in the loop, but that doesn't need to be the case. And this is quite controversial, but actually not so controversial. If we think about computer science, there are many ways of implementing a transistor. It's just that we've spent 70 years and trillions of dollars developing one type of approach using silicon-based semiconductors. And then we then make sure all our computations are compiled and use this physical architectures. So the question is, how do we make chemical machines or machines that make chemicals using a standard architecture to access any chemical reaction? So to do this, I introduced the idea of a chemical state machine. Now, a state machine is really a very basic object. It is a machine that has well-defined states where you can switch from one state to another, on and off. In computer science, or maybe in a chemical state machine, reaction start, reaction finish, work up start, work up finish. And I set about building a state machine for this physically. Now, to do this properly, to make a universal state machine, we need to basically represent this graphically, conceptually, before we build the physical architecture. So here, you can see on the left-hand side a representation of the digital inputs into our chemical kind of system, our computer, which has a series of physical inputs, right? Reagents, chemicals that are made up in the laboratory. There's a graph to describe the relationship of those chemicals in the hardware. And then you have the hardware, which has an address, and then you physically output products. And so this is done in the state machine here, which you can see has a scheduler, then can execute moving from one state to another by physically loading in reagents and energy or removing energy. And this is done by a digital control system. And then physically you have some flasks, some pumps, reactor, hot plate valve, and then you use this graph. So to build a chemical state machine is quite hard because you need to bring computer science, mathematics, engineering, digital electronics, robotics, and together with synthetic chemistry and mechanistic chemistry as well. So the abstraction of chemical assembly is a state machine that can make any molecule, material. The inputs are digital and physical, and the outputs are physical. And to some degree digital, because you'll be recording information about the representation of the molecule to basically digitally assign it. So seems like a long time ago now, about 7 years, we started to build our first computers. To do this, first of all, we started building our own pumps and valves. This may seem a bit silly because it's very, this type of hardware is getting cheaper and cheaper. But I needed to build the first pumps and valves to almost like build like my own transistors, if you like, to start to build an architecture that I could program. Because it was very hard to basically have the right hardware that we could interface to software without some problems unlocking from the vendors. At the same time, we made the schematics for the different components, the reactor, the digital control system. We built all the electronic boards in Glasgow, designed them, and they had some quite interesting features. So to make a programming approach to any known synthesis, any known molecule that has a synthesis you can write down, what we tried to do is build a synthesis reader, which uses a natural language processing system to take the literature. And then we then read the literature to try and build the most fundamental universal reactor that could basically make any molecule. So the way to do this is take all the literature, every single paper ever published in chemistry in the last 200 years, read the process, encode the molecule and the outcome, and then show how we could make this work on a chemical processor by having a virtual machine, compiling with a graph, checking everything works, and then running this. And the way we do this is we have an integrated development environment, chemical IDE, for which has our synth reader. We then have a synthesis development environment, a compilation, and virtual execution. We produce the working files and then have an internal representation of the chemical code in KDL. So KDL is kind of like the machine code of chemistry, and then we then run it on our virtual machine, and then the idea is to then to make it work in the lab. So this is the first computer we built. So what you can see, can you see the video running? Can you see the video running?
Yes, no problem, no problem. Yeah.
Okay. So now the process starts to do the 4 steps, which is the of computation. First is reaction. Every molecule, to make every molecule, we need to do a reaction. So the reagents are mixed in the reactor, and you can see the reactor is down here. And then after you do a reaction in chemistry, you have to do a workup. Now the workup can be very complicated and take on very many different features. In this case, we're showing a biphasic extraction. So you'll So the abstraction of chemistry is reaction, workup, and then after the workup, as you can see here, we then basically isolate our crude material. So the abstraction is now reaction, workup, isolation, and then in the final step of computation, you do purification. And so the purification in this case, we're showing as a crystallization. So we take the crude product, dissolve it in solvent, move the crude material to the crystallizer, and the crystallizer is on the left-hand side here under this gray-black box. And then by controlling the temperature, we can then cause the material to crystallize at the right temperature to produce the purified product. And so in this robot, which we can represent with this in this way, with this very simple kind of representation of inputs and processing modules and outputs, we were able to, in this case, you can see this component made here, we were able to make not just one molecule, but in this prototype, we made a number of different molecules, in this case, nitrile, rufinamide, and sildenafil, and we used one robot to make 3 very different drugs. And in this case, I think you had a 4-step synthesis, a 3-step synthesis, and a 2-step synthesis in this case for each of these compounds. But they all use the same hardware. They all use the same programming language. And so to make these different molecules, all you need to do is go to the robot and load in the reagents, and then load in the code, load in the graph, and then execute the program. And the robot even self-cleans. But to do this, to make it universal, we had to build a programming language. So I'm going to explain how we built a programming language for this, because it's really important for organic chemistry. So if I'd like to compare chemistry at the stages as represented on this slide. So here's alchemy. Alchemy was what the name that we gave to when chemists or alchemists 300-400 years ago would do chemistry in their own environment, and they had their own special tricks and representations. The language wasn't that universal. No one really understood how a bond was formed or broken. We didn't understand molecular relationships, atomic theory. So it was really a very strange representation that I liken to putting the first language in stone. So where people are starting to go. Then we come through to modern chemistry, and modern chemistry uses some well-defined rules, defined by atomic relationships, Lewis theory, then quantum theory, DFT, and we can now represent molecules using well-defined representation for the bonds, and then how we make and we break bonds, and we cause rearrangements in molecules and in reactions. And that I refer to as a bit like calligraphy, because you have to do it by hand. You understand the rules. You understand the rules of writing, and before the printing press, you had to write everything by hand. You knew the alphabet, whether it was Chinese alphabet or Chinese kind of representation, or English representation, or Roman, or whatever. There was an alphabet you used, but it had to be built by hand. Computation you should think of computation like the first printing press for chemistry, okay? And that's really important. And obviously now we want to go to this universal standard. So there's the programming code that we have, we call KDL. And what it is, it's a way of representing how to do a reaction for real in some hardware that uses the concept of the reaction, the workup, the isolation, and the purification. This is our abstraction of chemistry. For a computer, the abstraction is a Turing machine where you would have inputs, process, outputs. Okay, and there'll be an architecture for doing this. If you can take this example here, when we're making lidocaine, we start with this aromatic amine, and then obviously we add it together with this reagent, add in 2 further reagents. You have add, then filter, or for solid, then add another amine with a solvent and reflux, add heat to produce your product, lidocaine, which is an analgesic, wash, extract, filter. In a laboratory, a chemist would do these by reading the literature procedure, but if we're reading the procedure as represented, we have 3 moles of HCl, 50 milliliters was added. The mixture was then filtered, washed with water, dried for 2 hours. And so what we're going to do is we've now got this composite diagram where we have the unit operation of add, filter, wash, solid, dry. And we broke this into sub-steps and then base steps, which can be reused. So if you take this literature here, we can then read this and then turn it into the programming code for the chemist. Chemists could also produce it from scratch. It's hardware independent. Super important. It's hardware independent. You can have any robot you want. Okay? It's a linear sequence of synthesis steps. The fixed reagents, fixed amounts, but we have scaling, fixed process variables, Python for everything else, and then you have these composing steps for making the thing work. So this is where we were a few years ago. Let me show you how we make a automated synthesis using KDL. Let's take a synthesis from Journal of Organic Chemistry, paste it into our reader. The reader then turns it into the addition, the heat, the add. There is a linter, a programming linter, for the chemist to correct the code. So you're very familiar with this in Python or many other programming languages, JavaScript and so on, how you would then represent this. So this is literally our IDE for computation. Then we will then put in the graph of our robot. Where is the reactor? Where are the reagents? And then make sure we can then take our KDL code and the graph and compile them together to produce code that then could do the reaction. And we then check it in this case for errors. So the programming language of KDL, we're actually at KDL 3. We moved so fast. And KDL 3 is still secret, but it will be released very soon to make sure that we get as many people using it. But really the first version of KDL was what we call a description language. It was like a scripting process. KDL 2 made the transition to a programming language with its own embedded logical structure, garbage collection, memory allocation, hardware allocation. And this integrates with the Chemify database for automatic synthesis and expanding the database of molecules that are both known and newly discovered. So let's show, can we expand this, right? So when we went from the first computer, we realized we had a universal approach. We could use cheap hardware that we built in the lab, but you could use any hardware. You could use Chemspeed robot, you could use a mobile robot, similar to what some of you guys are using and Professor Cooper is using. You could use Chemspeeds, you could use robot arms, you could use automated reaction systems. But before we get to there, I just want to show here how you could basically make 3 very different types of molecule. This is up the top here doing midaboronate chemistry for Suzuki. And you can see the sequence of events here: add, separate, filter, dry, evaporate, deoxygenate, add, heat, separate, filter, dry, evaporate, catch, release, evaporate to produce the final molecule. Similarly, to make a diazurine. So we're doing this very reactive chemistry here to make this very interesting unstable molecule. And then we can do peptide synthesis here. And so peptide synthesizers already exist, very well known, but they only do peptide chemistry. In the computer system, you can do peptide chemistry and everything else. Everything else. And that's super important. So what else? So how does this look like? We can do protecting group chemistry. We can do heteroatom alkylation. We can do CC bond formation. We can do multiple component chemistry. We can do library generation, and we can do multi-step synthesis. And in the computer last year, we showed we could do all this chemistry represented here, some 50 reactions in the hardware for real. And we released a database of code where you could download the KDL files and run them on computer here. So all of these reaction conditions, all these transformations were done for real in the hardware. And so statistics for the hardware, we had to obviously validate and benchmark. So this is kind of like we took the literature, translated the literature, and then validated the literature. This is a really nice way of saying what chemical literature works, so we can then use this as a basis for discovery, okay? And then there's some statistics here of the total number of chemical steps done in the hardware, which is about 1,000, number of unit operations, about 14,000, the approximate runtime, about 1,000 hours, average steps procedure, 20, average unit operations per procedure, 266, approximate runtime, and you can see that really how that works. So in this case, the paper we published in Science last year, we made 100 KDLs, 50 molecules synthesized, 1,061 chemical steps, 14,000 unit operations, 1,000 hours runtime. One of the big criticisms that we got when we were doing this from the organic chemists who were very grumpy and don't want to be replaced by robots is to say, which is kind of crazy because we're not going to replace the chemist with a robot. What we're going to do is make more molecules with a single chemist than we can now. But we then implemented a chromatography system so we could have end-to-end, input the reagents, and out we get a pure material, all using KDL. So we could basically have a ChemPU control the synthesis, chromatography module, we prep the run, sample inject, return the products, as you can see here. We've kind of made this modular system for not just normal chemistry, for photochemistry, for redox chemistry, bioreactors, solid reactions, high throughput chemistry, microfluidics, chiral chemistry, catalyst discovery, cell interface, formulation, nanomaterial, polymer and gels, and kind of to try and show that we could do all of chemistry, not just a small subset. So to program the chemical synthesis in general, what you have to do is take the synthesis procedure, translate into KDL code, execute the KDL code, get the experimental results, validate it, check the analytical chemistry, add to the database, and then this database should be a bit like a software Git, a repository for executable chemical code, not an ELN. I hate ELNs. Electronic lab notebooks are useless. We want to have a proper database, proper repository for running code. So let's now move on to platforms and algorithms. It's okay having robotics and hardware, but if you want to do robotic chemistry and then use modern mathematical techniques like machine learning and other regression approaches, we need to have some universal platforms. So one of the things I've been doing as well is building optimization for reaction discovery. So we can encode the reaction because now we have a programming language. Now we can optimize that programming language, update the parameters, and to do that we had to build a load of different sensors and then implement them for looking at, say, set the change in temperature, change in stability, charge in RGB, change in conductivity and all that. And then encode that in our setup here. So we have our KDL code. And then this is why the KDL needs to be a programming language, because then we can use logical statements in the program. Like if color change, then do this. If bubbling, so you have this kind of if something happens or when something happens, then execute something else. So you have this dynamic processing ability. We did this, a few examples here to do UGI reactions, Van den Duijsen, oxazole synthesis, manganese catalyzed epoxidation, trifluoromethylation, and a few other kind of reactions. We then also looked to try to learn reactivity, which is super exciting, using neural networks. And something that has just come out is we've done extensions to this using Bayesian inference. We're able to make a robot that discovers Nobel Prize winning reactions, knowing no chemistry. So we have a robot in the lab that's able to do chemistry, and it discovered on its own with no information from literature, Wittig, Suzuki, Heck, Wittig, Buchwald, Hogvig, Oldar, Monnick, Sonic and Shearer reactions on its own. And so this brings me kind of to, you know, the important part where we want to do discovery, not just in organic chemistry, but in material systems. So can we build robots, computers that do more than just do organic chemistry, but can do, say, in this case, soft matter chemistry. So here we have the first ever robot that we built to do artificial intelligence robotics on droplets and formulations. We also used KDL to basically mix together different materials and view them using image recognition and video to make new types of formulation. So in this example here, we wanted to basically explore a formulation space using this case a genetic algorithm to see how we can make highly unstable features. And this is part of my Origin of Life, artificial life work. Of course, life requires organic chemistry, but it also requires some other kind of capability. We built fitness landscapes to explore the droplet chemistry using evolution, and then to kind of show, again, using image recognition, how we could then keep track of the materials and look at the environmental interactions to kind of really explore all the chemical space. Now, what I'm going to do now is, like, I've only got a few minutes left, I think, maybe 2 or 3 minutes before questions. I'm going to go through a whole bunch of robots really quickly. So please don't be worried. I can send the slides. It's just a representation of all the work we've been doing in the lab to show how these modules come together. So kind of one of the things you want to be able to do is design experiments to basically do inorganic synthesis, so like in computation. So this example here is looking at crystallization. Can we find crystals? So in the computer, it's like, can we do the reaction? Can we detect the reaction as finished and then isolate the material by purification? In this case, can we discover new reactions by crystallization? In this case, polyoxymetalates, and we use an algorithm to explore that space very efficiently, and we can show the algorithm outperformed the human being. To do that, we had to build our own robotic workflow. So this had what we call a modular wheel and our own crystallization farm. And really all this hardware was designed in our facility because the chemists needed to design it all. You couldn't just buy the robot, you needed to make the robot. And this is one of the big things I want to say. It's okay buying robotics and spending lots of money. It's probably better to spend slightly less money and have the computer scientists, mathematicians, chemists working together. We'll also use this approach to basically discover energy materials. I'll give you one example here, where again we use the same module, electrochemistry module or pH module for then, and again this modular wheel for basically exploring different electrochemical processes, maximizing obviously the amount of charge we can pass. But really the point is we want to go use these standards to enable discovery, make and collaborate. The idea is to go code to molecules with experimental design, execute, look at the properties, update the KDL, and use machine learning to explore new chemistry. So in the final kind of few minutes, I want to show how we can do this with nanoparticles. So again, there's a lot here, but let me make a kind of quick, how do we discover a new type of nanoparticle? Well, measure its color, and then before we do the electron diffraction or microscopy or whatever you want to do. So we built a robot that could basically do closed loop nanomaterials discovery. The idea is you have you add some seeds, you then add some chemistry, you use the robot to do the reaction, look at the color change, and go around this cycle to make a closed loop system. This is the kind of approach we've got here, where we have this wheel, Geneva wheel. We do all the different reactions, look at the color change, look at the UV spectrum, and go around in a loop where we were able to explore 3 chemical spaces. And again, this is all encoded using KDL. Same with the formulation, same with the organic chemistry, and we could make better and better nanoparticles according to the specification.
Professor Lee, please.
Yeah.
Please pay attention to the time.
Yeah, well, I have 1.5 minutes left.
Okay.
Before questions, correct? Yeah, good. So then we can then use optimization and exploration to basically get to this kind of idea of making new materials, and then go through lots of different architectures. So, and then we then again represent the material synthesis using KDL. Now, this is a lot of information, but it's okay. I just want to show very quickly how we can put the KDL together to make these different nanomaterials. So what I'll do is go down to the last part. And so, let me just reshare it, because obviously this is a one failing with Zoom. When you stop your PowerPoint presentation, it takes it off. So this is really the summary of what we've been doing in the lab, using coding and hardware development for both not just organic chemistry, but formulation and material science. And the idea is to basically have this together where we have a universal platform for doing computation using KDL. But this platform universality means we don't just use the ChemPU, we can use SMS, ChemSpeed N9. It's task universal for synthesis, discovery, and optimization. And then we have chemical universality for doing any chemistry, materials, and formulation science. And I think I'm just on time. And I want to thank my research team in Glasgow. Lee Sanders, thank you for the opportunity for presenting, for listening. And I'm now open to questions. Thank you.
Okay. Many thanks to Professor Lee for his excellent presentation. Does anyone have questions?
Really amazing. I have listened to the talk for many times, and every time you just shocked me. Very amazing. And Professor Lee, I have a question. Actually, a lot of questions, but I just ask one. And you mentioned that in the beginning you do the linear sequence for the reactions, and in the future, I guess you are able to do the parallelized experiment. So, do you think it's possible to see that put everything together, even the different time control, sequence control, will change the way they react, and also change the byproduct, and also the production rates and so on. Yeah.
Yeah. So that's a very nice question, Jude. So the reason for having a programming language was to do exactly that, for parallel execution. So in computer science, parallel execution has been known for many years now, but in chemistry, we kind of don't really understand how to allocate it. We keep solving the problem imperfectly. And so by making KDL3 can allow conditional parallel execution, and it does it by resource locking. And so I developed all the mathematics 2 years ago, and now the mathematics and the process algebra is finished. And then later on this year, we'll be releasing KDL3, which allows parallel processes for high throughput. And we have got a robot called the OpenTrons, and we're able to do parallel chemistry and linear chemistry at the same time and mix it together using a scheduler. And this is very important. Now, I'm sure many research groups around the world are doing this right now, but I bet you that they are all doing it wrong. They're all doing it by hard coding, and not by using a architecture that is modular. And this is really important to have this. This is where the computing architecture is going to work out. So I want to publish this as quickly as possible, put it on GitHub. And so please, if you know anyone who wants to do parallel execution, please ask them to contact me, because I can give them the kind of conditional systems for how this works. So very good point. And yeah, so right now we can do probably about 150 reactions in parallel. We can also allocate all the resource in parallel, and we can also allocate the analytical chemistry in parallel and make it dynamic and conditional. And that's why you need a programming language.
Yeah, this is a new different level of chemistry. I think very amazing.
Yeah.
Thank you.
Okay, any questions?
One question, Professor Lee. Okay, Professor Lee, thank you very much for your wonderful presentation. The concept of computer and compute and the KDL you proposed is very innovative. And I noticed that the computer can automatically search the related literatures online and then transfer it to KDL. I wonder how it compare and choose the best reaction rules from so many literatures, and what aspects will the computer compare the literatures and the rules?
So I didn't quite understand what did you ask again? What it will compare what? Sorry.
Compare the so many reaction rules the computer search online.
Okay, so I think what you're asking me is how does it cope with lots of different reactions that are similar, and how does it compare them? Is that right?
Yes.
So the way we do that is like, obviously there are many thousands of different reactions, right? So there's a hierarchy of different reaction classes. So right at the base, when you're looking at what bond formation you're making, that can have one different label. And then as you change the variation, you get different labels. So what we do is, by understanding the bond transformation in the graph, we can then add on different process parameters that actually differentiates it. It's a bit like, I don't know, how many dialects of Mandarin are there, right? So obviously you have the base Mandarin, and then you have on different, like in English, you have base English and then different dialects of English. And so you have to, in chemical reactions, you have different dialects, and you need to make sure those dialects are captured. And actually using heuristics, not neural networks, you can do this very easily. And then by using neural networks to then help you make a model, a large language chemistry model that we have, then you can basically read all the literature and then translate that into all the different reaction classes. And it's really interesting because we're discovering new types of reaction in the literature that people didn't think would exist. So it's a good question. Thank you.
Thank you very much.
Okay, any questions?
I got a question. I got actually two questions. First, let me ask a practical one. When describing a standard experiment procedure with text like IDL, how do we know that we are using the if condition and other logic conditions properly? It could be overused, resulting in unknown problems due to complex logics, and also it can't be too simple to be fully functional.
Yeah, so when you'll see the KDL standards free, the logical representations are used very carefully to prevent people making highly nested representations. So the standard has been built from the practical backwards to make sure that we don't get into those complex environments. So although the language KDL is Turing complete, we do add some restrictions in kind of resource locking and memory locking, okay, and making sure those dynamic steps are executed at the right level of abstraction. And I don't know about your background, but you sound to me like you know some programming, computer science background. This is something we have to teach the chemists very carefully, because otherwise the chemists who are not necessarily experts in this type of mathematical representation will make something recursive when it needs to be just enumerable. We have to be super careful. Or enumerable rather than iterable. These are very small technical details that make a big difference. But the way we basically limit it very carefully, but we can then remove the restrictions if we need to under certain conditions. It's like any programming language. You have to do some restrictions so you don't do crazy things, so it doesn't run forever. But we don't want to make it too simple that it can't do any chemistry. Does that answer your first question?
Yes. So I see we need to set up some restrictions and then release them step by step to make sure that we find our final goal. Yeah,
correct.
And now for my second question, I think your work is truly amazing. We're looking at a machine just like ENIAC, the original gigantic computer. Maybe it's quite big, but sometimes in the future it can be smaller and integrated as into microchips. Is that possible? And what scale do you think the machine could be involved into in the future? theoretically?
Yeah, that's a really nice question. So I agree. I think this is the computer's the first kind of is the first like ENIAC for materials. So the problem with going with miniaturization in chemistry is that in computer science, miniaturization is fine because electrons are very small and you can represent at the limit a bit of information with just a few electrons. In chemistry, material science is scale dependent. So there's a surface area to volume ratio. There are certain scales at which reactions and materials transformations work, and certain scales they don't work. And so I think I decided that we would kind of implement it at a kind of gram scale, and we could scale down a little bit to make a kind of what we call a micro computer, and go up a bit to make a macro computer for kind of process intensification. So we have a microfluidic computer, but the problem with that is you have to control the chemistry very carefully. But it should be possible to go down to a few microns, and it should be in smaller scale, and it should be possible to go up to a bigger scale for manufacturing. So you have this connection. And right now we're just in that sweet spot. If you want my personal opinion, I would say always keep it around milligram to gram scale. Don't go down to nanograms because the chemistry doesn't work cleanly and controlled yet. But we might get there. And who am I to know where we will be in 70 years' time? 70 years of, I don't know, Cronin's law. Let's call it Cronin's law rather than Moore's law.
Yeah, thank you so much. I see. So it's actually the reactions that we are looking at decides which scale we are using we are designing the micro reactors.
Exactly.
And we are not going into nanoscales right now.
Well, you could at the end, but I would use the multi-scale modeling. What you could probably imagine is have multi-scale modeling, almost like a digital twin, have your reaction database, and then decide what hardware you implement at. So one day we could do single molecule manufacturing, but it'd be super expensive and probably not make much sense unless we were making antibodies or something. But let's never say never for anything. But for today, for our purposes, I would say you're exactly right. The reaction in the material defines the scale at which you need. So kind of say there are two questions. What is the minimum scale for discovering the material molecule? And what's the minimum scale at which you want to make it to be useful? And that they define everything else. So really nice questions. Thank you.
Thank you as well.
Okay.
So, Professor Cronin, because our next speaker is have a connection problem, so can I use the time to ask other questions? Another question.
Yeah, of course.
Yeah. So your analogous for the alphabet with the future development is very enlightening, and I'm thinking because as you said, the Chinese character is to contain the representation for the things, and the alphabet is use the sequence. So do you think it's possible that in your computer system, computation system, maybe the definition for molecule can be not only use the alphabet but also use the graph, like a graph neural network, to describe their connections and also groups?
So no, I think it's super important to not use a graph neural network to describe the process algebra. There's a very special reason for this. Neural networks can be used to kind of look at certain data. The problem with molecules and neural networks is using neural networks for any graphs is hard because they're discontinuous. There's actually what I didn't show, I have a few minutes to show, right? I mean, I didn't show this because I didn't have enough time, is one of the things we were doing is now, rather than having a graph for a molecule, we use electron density. And electron density is much better in a neural network because it's continuously differentiable. And so what we did is made a system for basically taking a smile from a molecule from an electron density. So you can have this process here where you have this electron density and you're able to make electrostatic potential, and then you have this kind of target output, so you can make a kind of guess representation. But I'm sorry I didn't cover this in the talk. I can talk about it another day, but basically in this case here, you're able to take electron density, generate some tensors, decode that, and then produce a graph in a smile. But in the KDL, in the description, this linear sequence of steps, that's just the way of just viewing the process algebra to make the molecule. You can have lots of sequences running at the same time. So I wouldn't use a graph neural network to kind of represent that, because graph neural networks are compressed representations of features. And in chemistry in the lab, to run a robot, you mustn't use a neural network. It's not like a self-driving car where it has to go from A to B. You need to precisely add the catalyst in at the right time. You need to heat it up. Chemistry is dangerous. And so in the same way, self-driving cars are dangerous, but they're simple. The car just has to not crash. In chemistry, so many other things can go wrong. You could catch fire, you could explode, you could clog, you could so the space becomes very, very complicated very, very quickly. Does that make sense?
Okay, I see, yeah. So the aspect sequence is more fit with the computer system.
Well, think about it like this. In a computer, you use binary code, right? And then on the top of that, you make a neural network. So using KDL as a basis, can you add neural networks on top? Yes. Can the neural networks be used to optimize reaction conditions? Yes. But they have to then go through a compilation system that goes into a finite state machine, because that finite state machine has to then control the state machine. We don't yet have neural networks that control the hardware. The only neural network we have that does that is in our brain, right? That's the only one. So you have to think about the representation layer. You have transistors, basically the logic on top of that, then on top of that, the neural networks. So think about it like this: computer, KDL, then on top of that, the neural networks there, and you can use that to do that next kind of processing.
Yes. So the basis should be on the precise control. That's the point.
Yeah. So think of KDL like microcode on a microprocessor, right? You don't use neural networks to put that, otherwise the computers wouldn't work. You need a well-defined graph for compilation. And the thing is kind of hard to explain to chemists. I mean, although I'm a chemistry professor, I spent, when I was 7 years old, I was building my own computers and designing them, right, from scratch. So designing the architecture, designing the address code and so on.
Thank you.
Okay, Professor Lee, since the presentation was also live online, many of the online participants asked interesting questions, and we have selected some of them. The first one is, do you think it is possible to extend the ability of peptide manufacturing to do protein design with computer?
Yes, we're doing it. So we can make insulin in the computer.
Oh, great.
So this is a big change. So one of the things I'm doing with my company is making a new type of peptide synthesizer for universal protein design. It combines three things: peptide synthesis, organic synthesis, any chemical synthesis, and ribosomal synthesis. So you can do ribosomal synthesis, organic chemistry, and peptide synthesis together. So that's a very nice question. And it's going to take some time to get the purification right. Purification is super tricky, but I think one day we'll be able to synthesize antibodies in a computer.
Okay, great. The second is, if there are unknown or unexpected byproduct in the reaction, can the NMR measurement tell the difference?
Yeah, so the byproduct detection is something that we have these optimization algorithms for. So you can use portable benchtop NMR or other detection systems, and byproduct control is super important in computing. And there will be an entire field of exploring, the chromatography and so on, and also how to use the byproducts to as reagents, right? So one of the big questions in chemistry is, how can you eliminate most of the byproducts or understand how to get to the theoretical limit? Because obviously some reactions are equilibrium controlled. Some reactions you can't push the entire way. They're not 100% clean. If you take DNA synthesis, there are some reactions now that are 99.999999% almost quantitative. Now, they are very special reactions, whereas you take some other reactions which are not so, the bonds aren't so stable. So you'll always have an equilibration, then you're always going to have some byproducts. Indeed, the byproduct is required to help you get the product. It's almost like you can't view them separately. So having that control in the future is going to be super important, and we're working on it. And I'd love to collaborate with people on that, by the way.
Okay. The third question is, how did you come up with the idea of studying computer? Because I wanted to make a machine to solve origin of life, the chemical. I wanted to make a search engine for chemistry like Google, Google. I decided I would take some robots and build some architectures. But then when I saw the robots that were available on the market, they were all too complicated to program. They weren't right for the chemistry. I then decided to kind of build a new architecture from scratch. And it took me a couple of years because I had to do that myself. And when I was doing that, I was a chemistry professor in a group when my group were chemists. So I had to do this in my spare time and just design the architecture and then very carefully take the architecture to my group. And then with my group, I then brought in computer scientists and mathematicians. And then over about, 10 years, I started in 2012. But remember, I was building computers using electronics when I was 7 years old. So 42 years ago. Great. Do you think it is possible for robots to replace humans in chemistry experiments in the future?
Yes and no. I think that the robots will replace a lot of the labor. But they're expensive, right? It's not just like a car factory. I mean, right now, you go into a car factory, there are robots everywhere. And making electric cars, I think in the end, an electric car factory, but chemistry is not making electric cars. Chemistry is about doing new reactions, making new molecules, having variations. So the human scientist is always going to be the center. And really, the computer is just merely supposed to be an accelerant. More molecules, make it cleanly, make it safer, make it more reliably. And also the most important thing is when a molecule is being made in the future, I want people to be able to download the code and then run that molecule, okay? Rather than this scenario whereby you have to read the literature, interpret it. So this precise transformation of the code to the molecule is the critical thing that we want to have happen. And so I think we're there. It's really exciting.
Okay, great. Professor Jiang?
Yeah. I'm sorry that we have problem to connect and the Coop from online. So it's kind of awkward. And so probably we have a short break and then wait for the connection to build.
Okay.
Okay, no problem, everyone. Thanks again for inviting me to give this talk. It was really nice to talk to you all, and I'm very excited to see what's going on in your labs. I think there's some very interesting big-scale chemical robotics going on in some of your laboratories just now. So please reach out to me if you want to use this programming language. I think one thing I would say is Eli Lilly in the USA built a very big automated chemistry lab about 20 years ago, but it was very expensive, many millions of dollars, and they couldn't replicate it because they didn't have a programming language. So one of the things we need to make sure is when you're building these big labs, that they use the programming language. So please use TiDL. It's free to use. It's an open standard. It's like binary. So just try it.
Yeah. I hope I can visit you in England in this coming months, because we are open now. So yeah.
Yeah. Good. Well, anyway, we're really nice to meet you all, and hopefully Andy comes soon. See you later.
Yeah. Thank you. Yeah. Bye. Bye. Have a good day. Yeah. 各位老师、各位同学啊，这个真的很抱歉，我们现在是怎么也联系不上那个我们下一位 speaker Andy Cooper， 他不知道是不是什么原因呢，就是这个电话断线了。那么电话断线导致他网络上面也没有反馈消息过来。我们其实之前是做过测试的，但是现在这个情况的话，我们只能说再等待10分钟。如果是那个再等10分钟他还无法上线的话，我们就可能只能那个改期再举办他的报告。不过没问题，就是我们可能就是在最近的1-2周内就可以再联系上他，再安排一系列的那个我们 AI Chemistry 的那个活动啊。正好就是我们其实还约了几位那个更多领域的那个 AI Chemistry 方向的这种那个领域的那个大咖，所以的话呢，就是把那个 Andy Cooper 的报告和后面几位那个大报告合在一起也是完全可行的啊。这个敬请大家期待吧啊。那我们先等10分钟，如果10分钟之后还是无法连线的话，我们就那个今天就很遗憾了，我们就不再进行这个论坛活动。好，非常抱歉了，我们还是无法这个在短期内那个连上与那个Andy Cooper 老师的那个网络，所以呢，就是今天就非常抱歉，我们那个 AI Chemistry 的那个最后一个报告我们就不得不改期。那么呢，改期时间的话呢，我们会尽快的通过那个税统与扣享的共享平台啊，向大家发布。那么Andy Cooper 老师的在那个 Robotic AI Chemistry 的方向的工作，大家都是那个听说过的，所以呢，我觉得还是值得期待的。然后我们后面的话呢，我们也会同时呢邀请那个我们正在那个接触的几位那个学术的大咖，那么呢，就会尽快的这个组织一期那个第2期论坛。同时的话呢，就再次做一个小广告啊，请大家这个多多关注我们的这个新期刊 Artificial Intelligence Chemistry。那么呢，我们的 scope 就是我们的范围啊，或者是我们的那个报刊宗旨的话呢，在网站上大家都可以看到啊。希望大家呢予以关注，也呢恳请大家呢多多投稿啊，也请多多支持我们的期刊啊，感谢大家啊。那么呢，就也祝大家那个周末愉快啊。好，谢谢大家。